Hi. Hi, Devox. Hi, people watching us online. It's a pleasure to be here. And my name is Oleg S, and this is Thomas Wuerthinger. And we work for GraalVM team at Oracle Labs at Oracle. And today we're going to talk to you about GraalVM, which is a very exciting project. How many of you have heard of GraalVM? Excellent. Good job, the GraalVM team. How many of you feel you can explain what GraalVM is? Well done. You are in the right place.
That's a bad job for the GraalVM team, and we're going to try to make sure that we use this session to that you can better explain that when you leave here.
Right. So,
thanks, Oleg. Yes. So, what is the idea behind GraalVM? I don't think one can understand GraalVM without knowing a little bit about the history and how it started and what was the motivation when we did GraalVM. And GraalVM actually started a very, very long time ago. It was 8 years ago that we started at Oracle Labs the GraalVM project. And originally it was really a pure research project, crazy idea, with only a few people working on it. And the idea was to create one virtual machine to rule them all. And what we meant by rule them all was like ruling all programming languages. Because we wanted to create one virtual machine that can run not just one programming language or one set of programming languages, but that can run any programming language out there. And the reasoning for that is, and we later changed the slogan a little bit to be less violent. We said like one VM to love them all, not to rule them all. But the idea behind it is that the programming language landscape is very diverse. So you have many, many languages out there. This is a snapshot from the TOB index, programming language index. And you can see like many, many languages are important. And the most important language is the one called others here. And so there's many, many more interesting languages like Scala, Kotlin, and others hiding in that others part. And so the idea was, why do we have like different virtual machines to run those? Why can't we have a single one? Because currently when you run a Python program, it will run on a completely different garbage collector, on a completely different interpreter compared to when you run a Ruby program or when you run a Java program. So the JVM has a couple languages that it can run, but still, JavaScript, Ruby, R, and others are not so well represented on the JVM. And the one reason why we did that was that when we started the project, I was before starting the project, I was working on the Google V8 team on JavaScript, and when I started at Oracle, I was thinking, why do we need two different compiler technologies running JavaScript and Java? And so the idea behind it is really, the core idea behind GraalVM is that it can run many languages with the same compiler infrastructure, with the same garbage collection infrastructure, and other parts that are usually separated when you run different languages. So the goal for us is that Graal is going to be the universal virtual machine that you will be able to use everywhere in the cloud stack and use it to run various languages, not just JVM-based languages, but others as well. And we have two goals here. One is we want to run programs more efficiently. So we want to make sure that the program is using less CPU cycles, is using less memory, is using less resources to achieve the same task. And the second thing is we want to make developers more productive. And the second part is, one of the ways we do it is by allowing you as a developer to run these different languages with the same infrastructure pieces. So you don't need to configure your garbage collector differently when you run a JavaScript application compared to a Java application. We make developers more productive by allowing you to combine programs of different languages. So you don't need to create a REST interface and network communication when you want to call from JavaScript to Java or the other way around. And the third part of making developers more productive for us is to allow you to write code in high-level abstractions and let the compiler and runtime deal with the task of making it efficient. And we will, at the beginning here, in the first section of the deep dive, I will show you an example of how the Graal compiler allows to write highly abstracted code and give you the same performance compared to as if you would kind of make it manually more efficient. So this is, in a nutshell, what was starting the GraalVM research project. And there's many different applications now. We will have 3 sections in this talk. We will have the first section will be on GraalVM as a just-in-time compiler, making JVM-based languages more efficient. Many people care about that. This will be the first part of the talk. Second part of the talk will be given by Oleg, who will talk about GraalVM native images, which is the ahead-of-time compilation mode of GraalVM, which is one of the aspects of the project. And the third part of the talk will be on GraalVM polyglot, meaning GraalVM running other languages. We'll give a status update of our Python implementation, our JavaScript implementation, our Ruby implementation, and our R implementation. And so this will be the third part of the talk and how we can intermix that. All right, so and with this, I give it over to Oleg for the intro.
Right,
now.
So as you heard, Thomas, GraalVM is a large project. It can do many things differently. It has a noble goal of making developers more productive and making software more efficient. How can it do it? It does it by being this high-performance polyglot virtual machine, embeddable virtual machine, right? So there are a number of qualities, and they allow GraalVM to be this versatile project it is. So you can run different languages on GraalVM, and you can run them in different scenarios. Like you can run this with a JIT, you can run it in the ahead-of-time compiled mode, you can mix the languages, you can embed GraalVM into other platforms. So it's a lot to take in. In one picture to explain all this, the general capabilities of GraalVM, probably would be this. The JVM languages can run on the JVM naturally, right? The JVM is the virtual machine for the JVM languages, duh. And GraalVM makes use of that and uses the JVM infrastructure and replaces the just-in-time compiler with the GraalVM compiler inside the normal Java hotspot VM, right? You can run it in the context of, say, OpenJDK. The other languages are implemented through several additional layers of infrastructure from the GraalVM project, but you can still run them on the JVM. Additionally, you can take the GraalVM technology, which is so far the main component that we've talked about is the GraalVM JIT compiler, and you can put that infrastructure into other platforms. Like, for example, you can, if we click, you can embed all that into a Node.js platform, right? Node.js is a platform for JavaScript applications. Normally, it comes with V8 as the engine for JavaScript. What we do in the GraalVM project, we take the Node.js and we put the GraalVM technology inside the Node.js. So you can run all the same languages within the infrastructure of the Node.js program, right? You will have the event loop, you will have the signal handlers that Node.js registers, you will have the normal behavior when Node.js cannot resolve a promise and everything crashes, and so on, right? You can also embed GraalVM in other native or Java applications, right? So Oracle has a large native application, the database. There are some experimental builds how to build GraalVM into that, and you can get a hold of the beta and try them. Or you can purely take the bytecode of your application, compile that ahead of time with the GraalVM compiler, the same compiler, just use this in ahead-of-time compiled mode, and you will get the platform binary, right? Native binary that will be platform-specific. It will be also small in size, and it will start up really, really fast because it doesn't need to do everything that the JVM does at the startup. So it can operate in a very different mode with different performance characteristics, right? So the project goals and the value that GraalVM can give you right now are the following. It's a high-performance machine for the JVM-based languages. So if you run Java, most of you, I assume, are writing or touching Java code daily, like 3 times a week. Excellent. How many of you are Scala developers? Not many. Kotlin? Yay, Kotlin gang. Perfect. Groovy? Anyone runs Gradle? Nice. Right, so there are a number of JVM languages, and recently we asked people what languages they're interested in. Clojure was a big favorite on Twitter. So, but like in a nutshell, by supplying a state-of-the-art just-in-time compiler to the JVM infrastructure, GraalVM can run Java languages, JVM-based languages, very efficiently, right? The second part of the value proposition is a low overhead, low footprint, ahead-of-time compiled mode. And we're going to spend quite a bit of time on that because it's a very interesting part of what GraalVM can do. How many of you have heard of the native image and compilation ahead of time with respect to GraalVM? How many of you think that this is the only thing that GraalVM does? Right? It's not the only thing that GraalVM does. Specifically, right? But it's a large chunk of what makes GraalVM so exciting in the ecosystem. You can have the polyglot tooling and polyglot systems, which might not be what you actually want daily, and you're like, man, I wish I could do this. But there are some use cases where this is very important. Like, for example, rendering server-side React applications. If you run Java applications and React, you can combine that in a single VM instance, and then you don't need to spend time sending data at the back and forth. And you can embed that into your systems. If you work on a large platform that offers some customization opportunities to your users, like you have a large platform, like maybe a data store, like Neo4j or something. Maybe you want your users to be able to use different languages to write queries. You can do that by enabling the GraalVM inside your application. How do you get a hold of all this goodness? Good news, you can just go and download the binaries. GraalVM is an open source project, so it comes with 2 flavors of the binaries that you can currently get. One is the community edition, which is built from the sources available on GitHub. They're all with permissive licenses. You can download that. You can clone the source. You can build it. It uses a maybe less conventional build system called MX, but it's open source. You can figure it out, right? It's just running a few commands. Or you can just download the binaries. And also there is the Oracle GraalVM Enterprise Edition thing, which is a product, and you can download that for evaluations from Oracle Technology Network and try it. And it's also free on the Oracle Cloud. So if you want to try this, maybe one good way to try it is to check it on the cloud. Right. The internal view into this, just to give you the scale of the project. Thomas said that it started like 8 years ago. And often people think that, maybe this is a small add-on to the JVM, right? It's not exactly that small. So GraalVM team maintains a number of projects across different repositories on GitHub, right? So we have the language implementations, quite a bit of them, right? And they take almost half of the code that we maintain. There is the compiler. There is the Truffle, which is the framework for for creating programming languages. There is some tooling, and there are some others, right? So all in all, it's 3.6 million lines of code, which is a very substantial project. And with all that, right, all those projects are kind of like subsections within the GraalVM large picture, right? But they are serving as individual components that enable different things. For example, to run with the JIT, you most probably are interested in the compiler, right? In that large blue squarish rectangle, right? If you are working with different languages, maybe you need to turn your attention to the language implementations. It's mostly, almost all of that is written in Java, which is a very good thing for Java developers, and me specifically. I feel like I can read and understand Java code. Normally, virtual machines and compilers are written in different languages with their different syntax rules and the reference operations, which I never can remember whether that is a star or ampersand, but you can go and look at the source code, you can check it out, and you can build it yourself, download the binaries, try it, and you can try to replicate maybe some demos that we will show you when we try to explain the technology deeper. So we're going to start with the performance demo with the using GraalVM JIT compiler. And Thomas takes it from here.
Yes. So as Oleg mentioned here, this is kind of also to explain again the agenda for today. We will move first to the compiler parts, which will be right now. We will talk about the compiler parts, which form the core of the system. And this compiler is the same compiler that is used in all configurations of GraalVM. So we use the same just-in-time compiler when we run. We use the same compiler when we run just-in-time versus when we run ahead of time. It's the same compiler phases, just slightly modified. And so the compiler is kind of the core piece that is reused on many places. And then later on the ahead of time compile session, which is the second session of today, we'll talk more about Substrate, which is our minimal virtual machine that is used when you compile to ahead of time. And then on the third part, we will do the polyglot things with all the languages. But yeah, let's talk about the compiler first. Oleg already mentioned the compiler is written in Java, so any Java developer can actually look at it and understand it. And the compiler is written not just in a stripped down Java. It's written with real object orientation, so with interfaces and everything associated with that. And this is called a deep dive session. So we will go now deep into the compiler parts to the point where we will show the assembly bits on the screen and the source code in the compiler that is responsible for producing those assembly bits. So this will be now the more technical part of the session, and we'll do a small demo on this. So for the demo, I actually have here, let me just show 2 more slides because this is preparation for the demo. The whole motivation for this is, I have here a tweet from Chris Newland, who's a Java performance expert that I respect very much and has written a couple of books also on Java performance. And I had a little argument with him on Twitter of how you should write performant code. And his bottom line in the end was, I tell my developers that hot code, meaning code that is performance critical, should look like it was written by my 9-year-old. No functional or advanced object orientation. So this is kind of, like when I read this as a compiler constructor, I feel very sad because I feel we failed our profession. Because as compiler constructors, one of the goals that we have is that this is not true. That you should be able to use high-level abstractions, but the compiler should figure out how to make them efficient. And that's like the GraalVM vision of you should be able to write abstractions without performance regrets. And as example for the demo, I have another example from a Twitter exchange I had with somebody from JetBrains, where he's asking can Graal eliminate array creation and boxes in a call to objects.hash and make it as efficient as the manual version of this call? Because in JDK, in newer versions, there's a utility method for calculating hash codes. And the question is basically, if I use this nice utility method, will I take a performance hit or not? If we now look at this utility method, and let's just look at this method maybe here.
Can you make it larger?
I need to make it bigger, yes. If you look at the implementation of this utility method objects.hash in the JDK, then it uses a variable length argument values object array, and then it calls arrays.hashcode. And when we go to arrays.hashcode, it will iterate over this object array and call hashcode on it. So this is a very general way to compute the hashcode of n values using modern Java syntax and these array creations. So what I have now here on my computer is I have a little micro benchmark that is, it has two fields, an integer field and a double field. And it is benchmarking the manual version of computing the hash code against the abstracted version of computing the hash code. For visibility, I've just copied the code that I just showed you in Eclipse here that does this abstract way to compute the hash code. So when you run this type of code now with, I have a couple Java virtual machines installed here. Let's just run it with a JDK 8 version for now, and I run this with gmh objects.hash. In order to make the results a little more reproducible, I disable the turbo boost on my laptop because that can otherwise add to the variability of results. It should work usually.
Nobody does that for sessions. It's a performance engineer talking. I would show it as this.
Okay. So it worked. So now it's yes, of course. So now my turbo boost is off, and I run this objects hash, and it runs first the abstracted version here now on stock JDK 8, and I get about 138 operations per second. And then I run my manual version, and it's like 4 times faster. Here on standard OpenJDK 8, the manual version of the code is 4 times faster than the abstracted version. So by not using the objects hash abstraction, I can get 4x speed up, right? And if I now run this same piece of code with the GraalVM Community Edition, let's take this version, one of the latest versions here. Then this is Community Edition, by the way. This is the free available Community Edition. And we see with GraalVM, wow, the abstracted version is actually like same speed or like even 1% faster than the manual version on JDK 8 here. So this is an example where GraalVM's optimizations can help to have the abstracted version of the code be the equivalent speed of the raw version of the code, and compared to with the previous results where this was a huge difference between the abstracted version and the raw version. Like here, the difference 4 times difference. So okay, so that's all nice, but I got the feedback from the talks. You always show them like this is faster, but like you never explain why. So this time we will go a little bit over the actual performance optimizations that the GraalVM Community Edition compiler is doing on that piece of code. And for this, I will start first with the Java code showing this because it's a little bit easier to understand, and later I will also show it in the compiler graph. But let's just first think about it. How would the compiler optimize this piece of code? And the first thing to note about this piece of code, when you write it like this in Java, the actual bytecodes that the JVM will have to run look like this, because this is a variable length argument method. So in the bytecode, it is allocating a new object array, it is boxing the integer field, and it is boxing the double field, and it is calling that method. So this is really not a compiler optimization. This is just writing this code a little bit more explicitly here. One of the first things the compiler would do early on is inlining. So we will inline the hash method that does this hash computation into the enclosing method, and then we will have this piece of code to work with. And in this piece of code, actually, we already see one performance optimization that the compiler can do that even your IDE tells you already, because we see here this underlined return 0. The IDE already tells you this is that code. After inlining, it's that code. That's true, because we know we just allocated that array. It will never be null. So that's why the compiler can just remove this piece of code. That's simple. That's just usual dead code elimination. Then we get to this version 4 of the code, which is just an object allocation, an array allocation, 2 boxes, and the for loop. The next thing the compiler does here is one of these optimizations that is in the Hacker's Delight book. We multiply here with 31, and instead of multiplying with 31, what we can do is we can multiply with 32 and abstract the same value once. And because the reason for that is that multiplying by 32 is a very efficient operation, because we can do a shift left by 5. And this is more efficient on a processor. Even on a modern Intel processor, this piece of code is going to be more efficient than this piece of code. So the compiler is now exchanging this 31 times value with value shift left 5 minus value. The next thing the compiler can do here is it can unroll the loop, because we have a loop over an array, and this is really just iterating over array elements. But the array elements, the length of the array elements is constant. We know this is an array of size 2, so we don't actually need to loop over it. We can just unroll the loop completely and have the loop body copied twice. So we now have the loop body copied once for the array at position 0, and we have the loop body copied again for the array at position 1. So this is version 6 of the code now, and as you can already see in this version 6 now, we can now eliminate some more dead code here. Actually, the IDE somehow isn't clever enough to figure that out, but in this case, this if statement is also dead code, because we know that the array at position 0 is null at this stage. For the compiler to know for sure, it's actually important that we already know that this array wasn't shared with another thread, or another Java thread. This array is local to the current thread, so this array is initialized here with a new value, which is never null, and so we can eliminate these if statements here. So this is now version 7 of the code. After we arrived at version 7 of the code, we have another optimization to do here. We can actually, this boxing of an inline integer field and getting the hash code out of it is just the integer field. Because when you create an integer and you get the hash code from it, it just returns the value of the integer as the hash code. So we can just replace it with that int field. We can remove that actual boxing and hash code function. We can do the same thing on the double side, but on double there is still a little method call remaining here, and I will later talk about the content of this method. But we just eliminate the box and do double hash code directly on the double value. So now on the double value, and this is now getting a little bit complicated, but I will show it here. So double.hashcode. Let's go to JavaLang double and the hashcode function on JavaLang double. It's here. So what the hashcode does here is it does double 2 long bits. It converts the bits of the double into a long in Java, and then it makes a small calculation as to get the integer hashcode of that bits. And the method double to long bits is kind of complicated, more complicated than you would think. The reason for that is that it tries to give you the exact same bits no matter what not a number representation was the double itself. Because in double you have not a number as a value, and you have many different bit values that can mean not a number. So you can actually you have like a certain bit range where each of them means not a number. And what this piece of code here tries to do here in the GTK is making sure that whenever you are in one of these ranges that are not a number in double, you get the exact same bits back. So the interesting piece here is that, well, this is this piece of code, yes. And I just inlined it now here. But the interesting piece is the compiler does here actually something which is also interesting, which is it undoes a manual optimization. Because people in the JDK were at some point in time writing this piece of code and thought, this is a nice way to check whether we are not a number or not. And in older processes, this is indeed the fastest way to check whether something is not a number or not. In newer processors, this is not the fastest way to check whether it's not a number, because in newer processors, directly checking just this expression here is faster. So this is like this looks a little bit funny here, but the only value of double that is not equal to itself is not a number. So this is not a number check in double, and in Java as well. But this is one example where we as compiler guys are like looking at the code that was manually put into JDK and see, okay, this is actually not the best optimization for the current platform. And we kind of undo that optimization and do the not a number check directly by just comparing the double value. There is one more optimization that I kind of merged into here, which is because R is initialized with 0, this value obviously is 0, because 0 is shifted by 5 minus 0 is 0. And then in the end, this is the final piece of code that gets then converted into machine code. This is just walking you through the whole pipeline of things that GraalVM does on this piece of code. So what you can do with GraalVM is you can use a visualizer, and we have a visualizer for the compiler graphs of GraalVM, and we have like here a couple comments on the bottom that are showing how to invoke that visualizer. We are dumping at a certain level, it's level 2. We are printing it to the network, meaning like to the currently running instance of the ideal graph visualizer, and we are filtering only on objects that hash methods. And I've run this previously here to get the compiler graphs. So this is dumping level 2, so it actually only shows the higher level of optimizations. We can go to a lower dumping level actually here if you want. We can go to dumping level 4, and we can let this run in the background while I'm going here. So this is now showing a lower dumping level. This is actually maybe better to look at. Because here we already see that the Graal compiler, it's a little bit hard to read, I guess, but it's, yeah. So here we see that the Graal compiler is inlining a couple methods here initially, like objects, double hash code, integer hash code, etc. And when we look at this compiler graph, at the beginning of a method, at the beginning, when the compiler works with the compiler graph, it looks actually very similar to Java code in terms of its, if you would put the Java code into a control flow diagram. So you have like a new array, you have a load field of an int field, you have a box, etc., etc. So it looks very similar to the Java program. And only later on, this is before the phase loop unrolling. Here we still have a loop in the graph, so we have a loop node. We can match this a little bit with the optimizations that I showed earlier. But then after the loop unrolling, after the phase loop unrolling, we see that the loop is gone, and the individual versions of the loop are just in here. One interesting thing about these individual versions of the loop is you see here a type switch. It's a switch on a class. This is already a construct that is not known in Java, at least not yet. I think it might come at some point. But the compiler already works with something that's called a type switch, which switches on the type of an object. And this type switch shows here two keys, which is double, Java long integer. This is one of the things where the compiler has profited from profiling feedback. So we got here information earlier on that on a certain place in the code, we did have only Java-lang double values and Java-lang integer values. So this is where the profiling during the interpreter phase is feeding us information that we can then use during compilation, and to put in just the type switch here with a double value, integer value. And the final thing here is something that is called de-optimization. This is where the compiler encounters a case that is unexpected, and in such a scenario would revert the compiled code back to the interpreter. So the compiled code is only using the cases that it saw already based on the profiler, and if there's an uncommon case, then we de-optimize out of here. This gets further optimized down the line here, and after 185 iterations over the graph, not all of them did something, but a lot of them did change something. The final method that is then converted into machine code, or the final state of the graph that's converting into machine code looks like this, which looks very close to the this piece of code here. One difference you might notice here, we have an if statement in this piece of code, and in this piece of code there doesn't seem to be any if statement because it just goes straight line. And the reason for that is that we have a conditional node that will later convert into an assembly conditional move instruction without actual control flow. But other than that, we see here this shift left to 5 and the minus of the same value. Like this was this one optimization I showed earlier, where we, instead of multiplying by 32 this value, we are putting it shift left 5 and minus the value. Okay, so this is kind of the compiler graph. And at the end of this is still not machine code. There is still two important pieces missing. One is the actual instruction scheduling. The other is the register allocation, and then creating the assembly from it. And for this, we have actually a second visualizer for GraalVM, which is called C1 Visualizer, which was originally designed for the Hotspot client compiler. And this visualizer has now a slightly more textual representation of the code. So we can look at the code after something that's called low-level IR generation, LIR generation. And it looks like this here. This is a little bit, this is now a little bit closer to assembly. But you will see one thing here which is not like assembly code. You see here, for example, a sub, but the sub instruction is not taking actual registers or memory locations. It is taking virtual values, because this is the code before we actually assign physical registers to the instructions. And what we can see in terms of register allocation is that for register allocation, the compiler creates something that is called here like life ranges for every values, and then assigns actual registers to those values. And on a large method, you would see which values would be spilled and which would not be spilled. And then after the register allocation, now we are getting even closer to the machine code, where we have, let me see, somewhere here, after linear scan. Now we have actual registers allocated here. So here we have XMM0, which is a floating point register allocated for one of these comparisons. And we have here, for example, for this sub was allocated R10 and REX as the result. So now we see the actual registers. And this is now only a very small step then to the final code generation that then looks like Intel assembly. It's a little bit distorted here because it uses some Intel instructions that are not known by this visualizer. But here now, finally, here we have the sub instruction with the actual register EAX R10. And this goes now to the processor, and from here on now, Intel hardware guys need to take over what actually happens to the code. Okay, so let's go back up.
This is the deepest point of the deep dive.
That's the deepest point of the deep dive. We will not continue like this. But still, I wanted to show one time like the whole pipeline. We saw it now in the relative, like in the approximate code, how it looks like in Java code, how it looks like on the high-level compiler graph here. And than how it looks at the assembly level with the lowest level visualizer. These visualizers are, by the way, available online. You can download them. This ideal graph visualizer is available on OTN, on the Oracle. No, not this one.
Technology network.
GraalVM OTN. Here at the end, there is something called ideal graph visualizer. It's, by the way, called ideal not because we think it's ideal, but because ideal is the name of the IR from the server compiler, and this tool was originally created for the server compiler. Yes, we have a question here.
Yeah, are there particular optimizations that you showed that were not things that C2 can do? Like, what's different in what Graal does versus what the JDK compiler does out of the steps you showed?
Okay, so the question is, what is different, what Graal does in those steps that the JDK compiler does not? So in this specific scenario, the most important optimization that Graal does here that is not done accurately in the hotspot default compilers is the escape analysis of the object array and the associated values. And combined with that is that I think, I've not checked it for sure, but I think that it also doesn't unroll the array. So in the end, it has to allocate an array, box 2 values, and do that for loop. And and that's a 4x difference on this piece of code. In the case of the raw version, it does the same optimizations, and it is actually the case that the raw versions are very similar. It's just 1%. We are just 1% faster, but it's very similar the raw version. So it does the same trick on intensifying the double hash code function. But generally, it's always like hard to say because there is many optimizations here, and there is many optimization phases where something could go wrong, where maybe we allocate registers differently or similar, and then you have a performance difference. To show you that this performance is by far not granted, I can have here another virtual machine available. So here for Graal and C2, we had here 480 operations per microsecond. So, but for example, I have here a completely different compiler. Again, this is OpenG9 compiler, and I can run that same piece of code. And in this compiler, the abstracted version here is like actually 10x slower. It's even like about 3x slower than on hotspot, and the raw version is about 30% slower than hotspot. Oh, it's actually faster here in the end. Okay, that's interesting. All right. I guess that looks like cheating. Let's just run it again. Now I think there's something wrong with the JMH here. Yes.
Oh. We had a question from the audience.
What if we have polymorphic calls, like multiple different calls in our application with different signatures? Are we going to optimize only for the most popular one, or are we going to have multiple versions?
Right. So the question is, what if we have the polymorphic code, right? For example, and will we optimize for the most popular, the cold version, or will we optimize for different implementations of the polymorphic code cold?
Mm-hmm. Okay. Yeah. So when you have a virtual call, then you have a certain amount of types that you would like. It's about 3 or 4 depending. You would kind of optimize for the 3 or 4 most popular types, and then you would potentially still put in one generic case. but you would certainly only optimize for the most popular cases that you saw. And it can also depend on the it can depend basically how your application operates during startup, because the profiles are usually taken during startup time, and so that's why the behavior will be targeting or optimizing for what happened during startup. Right? But we would not, like, the optimization on specific types for polymorphic calls stops at a certain point in time, where, like, if you saw too many different types, if you saw like 8, 9, 10 types, then we would no longer do this optimization, because then the regular virtual call is faster. Yeah, so this is a JMH bug. I will, because this is suspicious that, like, during this exact point in time when from warm up to iteration it swaps. But we can also test something else here, which is I have one more virtual machine to test here, which is JDK 13 here. JDK 13 contents home.
While Thomas is running the benchmark, how many of you run Java 8 in production? And older, like 7, 6, and those? Like all together, 7, 6, 8, not newer. How many of you run Java 9? And, like, I guess 11 now. 9 to 11. A few, quite a bit, like maybe 30%, maybe 40%. How many of you are on Java 13? 13 is the current latest, right? In production. All right, nice. It was released just a few months ago, so we understand. I just...
Right, yeah. It will actually, so GraalVM currently is based on JDK 8, but in the next version, which will come out in 1 week or 1.5 weeks now, we will have a JDK 11 version for GraalVM as well. So you will be able to use both. Here I'm running JDK 13. It is giving a similar score for raw, but it is giving a slightly worse score even for the objects abstracted. This is one of the things which is important to know between JDK versions. It is the case that on JDK 8, the default garbage collector was the parallel garbage collector, which is optimized for throughput. And on JDK versions, I think 9 or at least 11 for sure, the default garbage collector is the G1 garbage collector, which is optimized for low latency. This is why when you compare, for example, a JDK 8 version with a JDK 11 or newer version, you need to be aware about the that you are actually benchmarking two completely different garbage collectors, and you would basically want to specify explicitly whether you want to use parallel GC or G1 GC. But generally, the performance is similar here.
Right, so how do you pick the best virtual machine for peak performance? There are different virtual machines. There are tons of code that you showed us, right? There are difference between, like, how you write the code, right? How to pick the best runtime for.
Right. I mean, so one thing, of course, is for peak performance, you want to put parallel GC in there for best throughput, if you don't care so much about your tail latencies. Well, yeah, I mean, for the peak performance, we have some performance numbers here, which are, I think, let's go back to the slides maybe, because I will have them on the slides here, for GraalVM Enterprise Edition, which I think show that we give the best peak performance in many scenarios. So, yeah, but to conclude here this deep dive session, one more deep dive aspect here that I want to show is I showed this optimization where the multiplication with 31 is replaced by the shift left by 5 minus the value, and if we can now actually, this is now the GraalVM compiler code. And it's written in Java. It's nice and object-oriented. I have here a multiplication node. It implements a couple interfaces. It uses generics, everything. And what we can look here is there is something that's called canonical, that it searches for a better version of the same node. And we have here something where, well, I'm called here canonical, where I'm multiplying with a constant. So my constant is the constant I. So I is 31. So I is none of those. So it's I is greater than 0. So if I is a power of 2, I can just directly go to a left shift node. And if I is a power of 2 minus, if I minus 1 is a power of 2, I can do this stuff here. But I plus 1 is a power of 2 in our case, because 31 plus 1 is a power of 2. And then I can create the subtraction node and the left shift node with the 2 logarithmic of the I plus 1. So this line of code is executed to do the optimization that I showed of the shift left to the multiplication to the shift left. And all of this code is also available on GitHub, so you can download it, look at it, look at how it changes. There's many changes going on the GraalVM repository, and you can like look at commits where we like do smaller changes to the compiler, where we do smaller. Sometimes it's also just like moving a phase. Like this was a change I did like 2 weeks ago. We would move certain phases because the phase ordering is very important in the compiler as well. All right, so on the just-in-time compilation performance of GraalVM, this is one of the larger benchmarks that we run with GraalVM that I think shows the performance characteristics on different workloads. So this is showing the GraalVM Enterprise Edition performance and the GraalVM Community Edition performance normalized against the C2 compiler, which would be the default high-tier compiler in the hotspot virtual machine. This is showing a couple modern web frameworks. Here we have Akka, some Scala code, but you also have some Java-related benchmarks here. I think you have Neo4j somewhere. And what you can see is that the performance is, like how much performance you get out of using GraalVM Enterprise Edition can vary a lot from workload to workload. So we have some workloads here, like for example, Akka UCT, where like there's almost no performance gain, like almost 0. But then we have some benchmarks where you can get a 2x or 3x. And this is also why it's hard for us sometimes to characterize, well, you know, just tell us how much faster this compiler will be. And it's hard to say. It's you need to test it on your own workload. We're encouraging people to have their own benchmark setups, and we can assist with making sure that the setup is reasonable, and then do those calculations. But what is important for us here is that, like here, GraalVM Enterprise Edition has no performance regression at all to the standard compilers in Hotspot, and the composite here is 32% faster. This is, by the way, on 19.0. I'm pretty sure we're already up a little bit further on 19.2 and 19.3, because we do continuously improve our performance between versions. But it's always a small performance improvement. Might be larger for your specific workload, but on average we always do small steps, because performance is a game of many small improvements then make up the large improvement. And the geometric mean here for the Community Edition is still 6% better, specifically for Scala workloads, or maybe also Kotlin workloads, like workloads that are more object-oriented. We often have also speedups in the Community Edition. Generally, we advocate for more benchmarks. We want to see more benchmarks from also real workloads out there. because the problem for us as compiler constructors is that if we optimize for too few benchmarks, it's like overfitting a machine learning algorithm. It's like you will do very, very good on the benchmarks you optimized for, but you give it something else and it's completely like bad, for example, right? So that's why we actually are discussing currently in the team to have like a set of test benchmark and validation benchmarks, kind of like what is usual in such scenarios. But generally what helps against overfitting here as well is just to test more workloads. And some of the benchmarks out there currently are for Java that have been around for a long time, and they are no longer that representative for what would be a modern Java workload. Or they are also not representative of the bytecodes that would be given to the JVM when you run a Kotlin program or a Scala program. So we started one project here together with academic collaborators. We call Renaissance.dev, where we have a couple of benchmarks open source with more modern Java workloads, and we encourage the Java community to add additional workloads there. So we can make it more diverse. So we have more data to understand and more data to work with when we test our compiler. So when we are doing every change in GraalVM that is merged is not only undergoing a tremendous amount of testing, it's also undergoing a lot of benchmarking. So we have like a little compute cluster where we spend for every merge like I think a month of compute time nowadays that will verify that this merge didn't regress any performance characteristics. So the bottom line is usually trying to test your own workloads. One of the things that we are often interested in is in such scenarios is to get Java flight recorder information. Java flight recorder information also tells us about how busy was the compiler during a certain run, which is another aspect here about like sometimes the compiler spends a lot of time on JIT compilation, but then once the JIT compilation is done, the program already exits. I have here one example here, the Java flight recorder information when you do a fresh checkout of the Apache Spark repository, and then you run Scala C on it, and then in such a scenario, you would basically compile all the time, and once you're finished compiling, your program already stopped. So this is a case where the JIT compiler is actually wasting CPU cycles by doing the compilation, but once the compilation is finished, the program already finished. And this is kind of what we then cover in the second part here, which is GraalVM's ahead-of-time compiler, where Oleg will move through the AOT parts of GraalVM, which can be interesting specifically for short-running programs or when you care a lot about a memory footprint. But if you care about peak performance of long-running programs, then GraalVM and specifically GraalVM Enterprise Edition is what we think gives the best performance. All right, so shall we make a short break, or you want to like move it?
Yeah, let's. It's early in the morning, right? Everyone is fresh and full of energy, so we're gonna continue. Good. Right, we're gonna continue.
Good.
We're gonna continue.
So we will move to your screen now.
No, we're gonna show the slides, and we're gonna move to my machine only for the for the demos, because they're gonna be demos. Right. So Thomas just covered in a lot of detail how the GraalVM JIT compiler works, right? Showed the phases, showed that you can write code differently to have different performance results. If you were more or less a sane human being, you would prefer to write like more maintainable code that it's harder for the compiler to optimize. And that was JIT. That was peak performance, and this is the second session on the ahead-of-time compilation, right? So. And this is we get into the area of talking about performance where different people talk about different things and often not understand each other, right? You find a Go developer, right? Somebody who writes in Go, and they would say that Go is faster than say JVM, right? And what they would mean that it probably starts off faster, it is easier to scale, in the specific cloud environments or stuff like that. They will probably not mean that it actually can outcompete the warmed up high-performance JVM, right? So performance means different things to different people. And when we talk to different people, we figured out that we should actually be very explicit about what we mean at every given moment when we talk about performance, right? So when we talk about performance, we can mean different things. Normally, it's usually peak throughput, which is what you obtain with the just-in-time compiler, because it has the best information, the best view into your system, into what your code is doing, into what data is flowing through the code, so it can optimize the best, right? Because it has all the data. It also we can talk about the latency, right? For many systems, latency is much more important than the throughput, because if you are serving a request for too long, you might lose a client. Right? You might not be actually in time to give any answer. So latency is another dimension of talking about performance. Also the startup. Many people care about the startup, and this is a dimension. The memory usage is definitely something that you want to keep in mind when you talk about performance, because nowadays we almost never run like a single version of the service, right? We write microservices, we run them somewhere in the cloud. We buy the compute power, and one of the most expensive things to buy in the cloud, in any cloud, is the RAM, the memory. Right? If you need to use more memory, you will need to pay more. Most probably for the general, like average use case, the memory will be your limiting factor for how much you can scale. So memory footprint is a very important aspect of performance. And the packaging size, but that is maybe not the most important thing. So if we talk about what the running a program in a JIT mode will give you, most probably it will give you the superb peak performance, the throughput, and it also will give you the best, probably the best maximum latency, because it will warm up everything, it will produce the most efficient code, and the most efficient code will probably finish the quickest. Normally, it will not be the fastest to start up because it needs to warm things up. It needs to collect the profile. It needs to do that initialization work. It needs to do the actual compilation while your service is running. So the values on the startup speed axis are a little bit smaller. And this is not to scale, right? Like there are no numbers. It is an illustration. However, if we talk about the ahead-of-time compilation, the picture is different. You will, since everything is compiled ahead of time, right? You literally take your application and you put it through the series of steps, and you get the platform binary as close to machine code as it gets, right? You can start it up immediately. So it will get great results for the startup. It will probably get good results, very good results for the memory footprint, because it doesn't need to include the compilation facilities anymore, right? If you compiled everything ahead of time, you don't need to compile anything just in time, so you don't need to include the compiler. You don't need to reserve the memory for the compiler. You don't need to make space for the compiler graphs and the data structures to collect the profile. You don't need anything of that, right? So you don't need to waste memory for those things. You'll get probably like smaller packaging as well, but what you kind of sacrifice a little bit is that your peak throughput will not be absolutely the best, because when you compile ahead of time, you don't have the luxury of having the most up-to-date profile. You don't know what data is flowing through the system, so sometimes you cannot just speculate and have some optimizations that the JIT will do. So peak throughput will be a little bit lower, and that is expected, and also the maximum latency would be lower, which is also expected because the latency is an inverse of the throughput normally, right? Unless we talk about different means of scaling your application, right? So this is the conceptual difference, performance difference between the solutions that will offer you the just-in-time compilation and the solutions that will offer you ahead-of-time compilation. It's a trade-off. For some systems, one is more important than another. How many of you think that peak performance is the most important performance characteristics for your workloads that you're working on? How many? Okay, like 4 people. How many of you think that the latency is the most important characteristic? Oh, more people. High performance trading, right? How many of you care about startup speed as the most important thing? Right, a few. Cool. Memory? How many of you buy cloud? Nice. So like even here, so just you don't see the whole thing, and especially people watching us on online don't see the audience. But there were kind of like almost half and half, the equal amount of people who were for peak performance or latency versus the memory consumption, and a few folks for the startup, right? So it was almost like an even split. The rest, I assume, are sleeping.
Yeah, but memory was winning, right?
I think memory was winning, which I interpret as people running stuff in the cloud and actually paying money to someone for running workloads. Right, so GraalVM, luckily, as a versatile project it is, this superb high-performance polyglot embeddable virtual machine, remember that phrase, offers you both solutions, right? So you can run your programs in the JIT mode, in the context of the OpenJDK or Oracle JDK, and you can also compile your applications ahead of time using the native image utility. And this is what we're going to talk about more in detail now. Right, so you use the utility native image, which is within your GraalVM distribution. You can find it there. And you feed it your Java classes and jar files. And then the result is the application that is executable, the native platform binary. What happens while it does this? So the native image utility takes your application, takes your dependencies, the libraries, the jar files that you feed it. It takes the classes from the JDK, right? Because it's also like Java code that your application will be running. And it takes the bits and pieces of the infrastructure from the GraalVM project called SubstrateVM, code name, never say that, call it native image. And it takes all that Java code and it feeds that Java code first to the analyzer, which analyzes what actually is reachable within, which code is going to be run, does the analysis, it figures out the bytecodes that will ever run across the whole stack, right? From your application through dependencies, through your frameworks, through JDK class library to the runtime bits, like a garbage collection. And it takes all that code and then it feeds that to the GraalVM compiler, right? And the GraalVM compiler looks at that Java code, at the bytecode, and just it would do normally used as a JIT. It takes that bytecode and outputs the machine code, right? And then it's all written out in the native executable. Right? While this initialization is happening, it also the native image pre-initializes some data structures and some parts of your application. And it can do more or less of that, and we'll see that in a bit. But what is important that your code and some of the data of your application end up in this binary on the right. And if we want a little bit more details about what is happening during the analysis, this is what it is. We look at the classes, we figure out which classes use other classes, right? When you write new a dot call method b that uses class commons from Guava or something, right? We figure it out. We run the initialization of those classes, right? We initialize the classes because they need to be initialized. And then we snapshot the heap, which means we run your application until a certain point, and then we put a stop into this. And whatever is in the heap, the object graph, it gets written into the data section of the native executable. It's not exactly the data section, but it is written in the final result, right? So if you initialize some data, or if you initialize the configuration of your application, it's going to be pre-written and pre-initialized in the binary. That will help to start up even faster and consume even less memory, right? If you need to read an XML file for configuring your application, and then your application never deals with reading XML files, it's just not what it does, right? It's all YAML after that. You will get stuck with the facilities to read XML files when you run it normally, right? Because you need to load those classes, they will be there, and then they will be there forever. If you need to do that once, you can do that while the image native image generation is happening, and then just consume the configured results later in the binary form, right? So it allows you even more optimizations for the startup. It also comes with it's a lot of flexibility, right? But it's a little bit harder to maybe understand what exactly it does, and it's a little bit harder to master it for your particular workloads. But the most important things that we would like you to know and recall when you think about the GraalVM native image are the following. First, the most important. This is not the only thing that GraalVM does. When people will tell you that GraalVM does something or doesn't do something, call them out. The second most important thing that the native image does is that there is a thing called closed world assumption. This is an assumption that at the image generation phase, when we produce this binary, when we compile ahead of time, we will see all the bytecodes that will ever run in the application, right? All of those are reachable, and no other bytecodes will appear out of nowhere at runtime. This is an essential assumption, and it's also a little bit unusual in the Java world, right? Because we expect that you can load any code from any URL and then load that into your running JVM, and that code can wreak havoc as it wants, or be secured by the security managers and whatnot, but it will execute, right? So under the closed world assumption, that is not the case, right? You need to specify all the code in advance. What it makes possible more aggressive ahead of time optimizations, right? If we know that the class hierarchy will not change, we can maybe inline something better, or maybe we can, instead of doing virtual calls, we can specifically link to the particular method implementation, because we know the class hierarchy will not change, right? So it's very important. And then it allows us to remove the whole infrastructure for compiling things at runtime. So all the dynamic parts of your application will require being configured at the image generation time. This is the direct implication. And also, the direct implication is that there will be no loading new classes at runtime. The closed world assumption. This is very important. What it gives us performance, and it gives us a little bit less than ideal developer experience with using the native image currently. It's getting better. The next important thing is the image heap. The image heap is the snapshot of the objects that your application created during the initialization. So it gets written down, and when your application starts, it is mapped to the beginning of the actual runtime heap. So it's a snapshot of your thing. It's a performance optimization, right? It allows us even faster startup, and yes, it allows us faster startup, right? So what you want to think about this is the following diagram, right? So normally you would compile your sources, you get your jar files, and then you will need to do quite a bit of work before your application is running, right? You will need to load the classes, you load the configuration, you verify everything, you start initializing the data structure for those, and then at some point you start running the workload. We're not even talking about getting to the just-in-time compilation, right? We're just talking about initialize everything before you can start running things. So with the GraalVM native image by default, right, the border between what is done at the generation time versus at runtime is a little bit lower, right? So you can, like, the classes are already loaded. And then what you can do, you can also provide some facility to initialize the application to like a better extent rather than the default. And then you will get the best application of the GraalVM native images. Right? Of course, you don't have to do that all yourself. Sometimes you can use a library or like a tool or a framework that will help you. And this is certainly doable. Currently, right? We've been talking about GraalVM for like almost. I am talking about GraalVM for almost 2 years now. Certainly, some people are talking about GraalVM for almost a decade. But right, so before in the past, it was a little bit more cumbersome. Currently, it's much more accessible.
Yes, and you can use one of these. There's currently like 3 frameworks out there that support GraalVM native images. One is Macronaut, one is Quarkus, and one is Helidon SE. And we're currently collaborating also with the Spring team at Pivotal because we want to make sure that GraalVM native images work with Spring. I think they have a talk
yes.
this week to give us feedback publicly as well. I think Sebastian has a talk to talk about the current status.
I think it's on Wednesday at 4-ish p.m., right? So if you don't have plan and you are interested in Spring applications, and since you are here, you're interested in GraalVM, you should be there.
Yes, and so but the current status basically is like when you want to use GraalVM native image for your web frameworks, use one of these 3, like Macronaut, Quarkus, or Helidon SE, But if you want to use it for Spring, give some feedback to the Spring people, motivate them to work even harder with us. And we hope, I think the target is 5.3, which is early next year, to run on native image. Yeah.
Right. How many of you are interested in Spring applications? Yay!
All right, I think
nice. Go to the issue tracker, sums up the issue. Their issue tracker. You can also go to our issue tracker, but
so there's already some Spring applications working as well. So Spring has 2 web stacks. One is based on Tomcat, the other is based on Netty. It's called WebFlux, I think. And so the one on Netty is performing quite well on us already. With the one on Tomcat, we are still having some performance issues on native image, because Tomcat is starting many threads, and this is at odds with some of the runtime characteristics we put on native image.
Right. We'll get to that when we have the demos. I think I even have the native image of a Spring application here on this machine.
All right.
Not production,
all right, let's go.
We'll get there. Right. So all in all, when you want to run the GraalVM native image versus running the GraalVM Java in the JIT mode, right? When the startup time matters for you, you want native image, right? Because it starts really fast, milliseconds, literally. If your memory footprint is important, native image is important for you, right? You would like to figure it out how to make use of it.
Yeah. One note to memory footprint maybe is that the memory footprint advantages come primarily from removing the memory needs for metadata, code cache, dynamic code cache, compiler data structures, and profiling data structures. So this data correlates with the size of your application, meaning the amount of code that your application is loading. So if you have a large application with many dependencies and very large jar files, the memory footprint advantages of native image are larger. If you have a small amount of code that you're loading, memory footprint advantages are smaller. What is not affected at the moment in the current version of native image is the memory payload of your application itself. So if your application has a payload where it is creating a lot of data structures, then these data structures will be the same size in native image as in Java Hotspot currently. And this means that the memory savings are really big if you have a very large application that doesn't need a huge amount of memory for the payload, then the savings can be 5x, 10x. It can be a game changer. When you have an application that has a large payload, then the savings are going to be smaller. So it could be only the 10%, 20%. So this is just to say here why specifically we have a smaller memory. And one of the things in there is that we are working to also reduce payload data structures, but this is currently work in progress. I mean, on the roadmap to native image, we want to make sure that we are also compressing data structures more generally, because it's the memory density in the end is nowadays processors not only translating to savings in the cloud, specifically when you're on Amazon Lambda or something, but also it is relating to peak throughput advantages, because the smaller your life size of your application, if it fits in the L1 cache or not, can make a huge difference. We had a question here.
Yes. Can I simplify your memory workings by saying that it's mostly the non-heap memory that is saved, and that the heap memory is the same?
Yes, so the question is whether it's mostly the non-heap memory that is saved and the heap memory is the same. I would say that is mostly accurate representation. Not 100%. There is some parts of the heap memory that we also save. Like on the heap, for example, would be reflection data structures, Java-lang class objects. On the heap could be some data structures that you needed during some static initialization that never get cleaned up. So it is some percentage of heap data structures that we also save, but I think it's the smaller part. But the off-heap data structures are 0 effectively. So they go to 0, and this is the largest savings, which is also why when you want to measure those savings, you should not use, in this scenario, you shouldn't use Java Flight Recorder or a Java measuring tool, because those Java tools usually just tell you what's the current heap that is used on Java, and it doesn't tell you what's the actual memory used by the process. We recommend to measure residence set size, which is the actual memory currently mapped by the operating system for that process. One thing about that residence set size is that it is dependent on operating system heuristics, and it can vary over time. So when you measure these values, we recommend to use PS Record, which is a tool that is measuring the value over time. So you will see kind of how it goes up and down, and so that's relevant here also for a fair measurement, because if you take the value in one point in time, you might just get unlucky with the current residence set size of that process. And one final note on residence set size is it can depend on the garbage collection settings, meaning max heap size, initial heap size. Can have a large influence on this residence set size, which is why we also recommend to make sure that you have tried out different max heap size and initial heap sizes for your application before concluding this takes more than this.
Excellent. There is one more question there.
Is GraalVM also suited for applications which create many short-lived objects? So a lot of GC is needed.
Mm-hmm. So GraalVM.
The question was whether the GraalVM native image works for the.
The question was whether GraalVM is suited for applications that create a lot of short-lived objects. So the answer to this is that the GraalVM JIT mode is crushing it in such a scenario, because we specifically in JIT mode might have more abilities to even not have to allocate those objects, because we have the best escape analysis, meaning object virtualization, available in GraalVM. So what we see actually when we see people measuring the GraalVM JIT mode performance is that they sometimes get like, actually this is from the Oracle Cloud Infrastructure team, they have like 10%, I think the peak throughput was better on one of the core services, but the garbage collection times went down by 25%. So we actually often see the case where, we've seen this now in several scenarios, where we reduce the average garbage collection times more than we improve on the throughput. So lots of short-lived small objects, GraalVM JIT mode. So the question for GraalVM native image in ahead of time compile mode, generally short-lived objects aren't a problem for this one either. One thing to note here is that you sometimes will have to give a different configuration for your new space size. So new space is kind of the garbage collector in native image is also generational. It's like new space, old space. And what you should make sure is that the new space is large enough that most of those short-lived objects already die in new space. Because once you have to copy an object from new space into the old space, then it becomes expensive to later collect it. When you never have to copy the object into the old space, then the allocation is very, very cheap. And the new space size is the option for this is minus xmn. So there's ms, mx, and mn for new space. And in such a scenario, the native image garbage collector would also perform very well. But I would still think that the JIT mode with its better way to, I mean, we have the escape analysis also in time compiled mode, but I think in JIT mode it will do even better.
Right. This is the last question we'll take in this section, please.
What about writing the static analysis native image to a Graal JIT mode? So you're doing a static analysis ahead of time, so you could benefit from this analysis inside the JIT dynamic mode.
Mm-hmm. Okay, so the question was, why aren't we using information from the static analysis also in the JIT dynamic mode, right? So it is possible. One question for us in these scenarios is, are we allowed to rely on this information or is it only a hint, right? So in order for the information to be really useful for our JIT throughput, we would have to be able to 100% rely on that information. Meaning if you would then later load a class that wasn't known at the closed world time, the JIT would wouldn't be able to recover from that. I think the way to think about this is like a little bit the other way around, meaning what we are trying to do in the GraalVM team is to remove the limitations of the ahead of time compile mode and use profiling feedback in the ahead of time compile mode. So currently we think of it rather the other way around, like trying to make the ahead of time compile mode as good as the JIT mode where we're currently lacking, rather than trying to make the JIT mode use from this ahead of time compiled information, specifically because one of the main benefits from the ahead of time compile mode, and I think the survey in this audience showed it as well, is not necessarily the startup, but it's the memory footprint reduction. And this is also our biggest difference with other ahead of time compiled approaches, like the one currently implemented in Hotspot and in OpenG9. So they also have, there's like Hotspot AOT, I think the Microsoft blog was recently talking about that. So the Hotspot AOT and mode is helping with startup, but it doesn't reduce the memory footprint. And it is, by the way, also using the GraalVM compiler to create the code for this Hotspot AOT mode, which is another application of the GraalVM compiler. But we think the main advantage of AOT is the footprint. And therefore we think we would rather make that one better. The other thing is that on AOT mode, another major advantage I think that people are currently underestimating is the predictability of performance. We see this in our benchmarks ourselves. We often we're testing a lot of workloads, and then we have a couple of workloads that would alternate between two values. Like either we are this fast or we are this fast. And that's the peak performance. After we warm up for a very long time, we either get into this state or this steady state, right? And in many of these scenarios, the reason for that is that like, oh, maybe you're just unlucky doing profiling somewhere during startup phase, because it's very timing sensitive, and we have a lot of threads that would gather that profiling feedback in unsafe ways for performance reasons. And so what you get here on the JIT mode specifically is like, we have like benchmarks that have like 20% difference in peak throughput depending on how I started the app. And this is another disadvantage here. And with the ahead of time compile mode, you can make it predictable.
Right.
All right, cool. Let's go to the demos, right? I mean,
let's go through a few more slides,
yes,
because
okay.
this is very important. Now, like, everyone is pumped up. Everyone is ready to save memory and impress their friends and colleagues with the like millisecond startup times of their applications. Good. How do you make sure that your project actually works well with the native image utility? Very simple. There are a few rules. I'm going to go through them very quickly. The main point is, again, as we mentioned, probably you would just like to use a framework that figures out things for yourself. But if you are building a framework like that, or if you are starting from scratch, a few tips. First, you want to disable, there are like command line options. I'm going to show it. There is, if you unlock the expert list, the list of command line options you can pass to the native image is tremendous. It's like horribly long, because you can control the compiler as well. But first, you want to disable the fallback image. The fallback image is something there that allows you to run arbitrary applications, right? You want to disable that to get the best performance benefits. You want to use the flag report unsupported MLs at runtime. What it does, it makes your application blow up at runtime. By default, the native image would be very strict. If it will find something that it is not satisfied with, like a class is missing, or like some linking is not figured out, right? Or some code that it cannot like handle, it will tell you, because it wants to be rigorous and safe. Right? If you want to jumpstart your thing, you would like to say, like, you know what? Maybe you cannot handle this one class in this random dependency that I'm not even using directly, right? Report that at runtime, and then you run your test suite, and you probably will not even hit that code. So it might not blow up in the runtime. But you want to defer the problems until runtime to get started. Of course, when you go into production, you would like the other way around, right? You want to know all the problems as early as possible, so you will remove that. But
and so the reason for this flag is that like sometimes we have some piece of code that we cannot really prove that it's never reachable, but you might know that you're not reaching this code.
Yes.
And then you can put that in.
Like optional dependencies or something. Like you're loading Groovy jar file because you are using template engine that supports like Groovy. You might even not know that you're actually having that on ClassPass. Right, so ClassPass, another thing. Sometimes you have optional dependencies, right? If the native image will find the class that is trying to be accessed, but there is no such class on the ClassPass, it will stop. It will tell you, no class, I need to see all the bytecodes, right? Closed world assumption, remember? Like all the bytecodes. If the bytecodes are missing, what you get an error. So how do you deal with that? You allow incomplete ClassPass, right? Another thing, closed world assumption, right? Everything needs to be known ahead of time. And then some dynamic features. Sometimes you generate dynamic proxies. Sometimes you access data reflectively. Sometimes you do what? You use JNI. Sometimes you access resource files, like normal files, like HTML files or JavaScript files, or an image, God forbid, right? You are not using them as your normal class files, right? You are not doing like my image dot something something, right? You get class loader, get resource, and you get the bytes, and you send those bytes to the client. The static analyzer cannot figure out that you are using those by itself, right? It's impossible because they are dynamically used, right? So what you need to do, you need to provide hints to include certain things, right? Like resources, or to include the facilities to do the reflection on certain classes. You can do that manually with a simple JSON configuration file, or, which is the better way, is you can run your application on the JVM, normal Java process, and you can pass the Java agent file that will record the usages of those dynamic features, and it will provide the configuration for you, right? So you don't have to write that by hand. You don't have to actually know all the places where you do reflection, but you can still configure that. So the thing to do that, you say agent lib, native image agent, and you put the path where to put the config, and then you run as many scenarios for your application on the JVM. Right.
That is actually generally, I think, a useful tool for also performance analysis, or like just making sure you understand what your application is actually running.
Right. And in general, it's very useful to test what your application is doing and whether it blows up or not in any mode.
Yeah.
Right.
If you find a lot of strange classes being loaded, you might have some other issues as well.
Yes. So a little bit more information. The incomplete class path, more information about that. We are not exactly running out of time, but I feel that we should get to the number a little bit quicker.
I think
so. Just that.
Because also, like nowadays, I think, I mean, if you're an expert user, yes, this is relevant for you, and also come talk to us directly if you want to make your framework work with native image. But for regular users, I would say that the best way is to just use one of these frameworks, and then you shouldn't have to deal with this directly.
Right. And one thing that you probably will still need to deal with is the tracing agent, specifically for the reflection configuration.
Right.
How many of you have heard that GraalVM doesn't support reflection? Yeah, this is wrong. Like, no. First, there is a JIT mode that supports everything, right? It's a normal Java. And then there is a native image that supports reflection, but you need to configure that. So now you, 17 people who raised their hands, are cured of that misinformation, right? So the tracing agent is the Java agent. You run it. It records the configuration for you. You can manually then add to that configuration or change it if you want, but you probably need to run it for at least one reason. Normally, you will have like your data model that will be either enhanced by the data access frameworks like Hibernate or something that to create proxies that your data classes will be used in conjunction with the framework, right? So those are dynamic features. And then sometimes you take your Java objects and you want to serialize them into JSON to send somewhere, for example. Normally, some JSON serialization libraries also do that with reflection. Sometimes they're not. There are other approaches as well. But most normally, probably, if you just like slap a random Java project and there is a JSON serialization thing inside, most probably it uses reflection. So since no framework can deal with your model classes, right? They don't know your model classes. You might need to run the tracing agent. The cool bit about that tracing agent that it's a native agent. It's native code, right? But it's also written in Java, and then it's compiled as a native image of that Java agent, and it becomes a native agent, which is absolutely incredible. Right. There are a number of articles on the GraalVM team blog, which is the medium.com/GraalVM. So there is articles by the people who actually work on the native image technology about the class initialization changes or how it runs or the additional points. So look at that. Right. So if you have problems and if you see weird errors about class initialization or that there is a thread in your heap, image heap, or something like that, so there are two things that you can do. The first and most obvious is to come to the GraalVM community Slack workspace and talk to the team, right? Or raise an issue on GitHub and ask a question. The second thing that you want to do is you want to use the flag trace class initialization while you're generating your native image, right? We initialize some classes. Some classes can initialize other classes. And it's not obvious, not always obvious, how this initialization chain is happening, right? So you can be stuck with a strange error saying that, oh, there is a class that is having a thread initialized, and you cannot have threads at the image generation time, because that thread will not survive going from generation to production to the runtime, right? There is a strict border. The same is like reading configuration files. Most probably you want to read configuration files in the beginning of your runtime or initializing random seeds, right? It doesn't make sense to initialize random to a certain thing at generation time to always output 4.
Yeah, and in many scenarios, like some of these issues are really not that good designed by the code. Like if you start threads in static initializers, it's certainly not recommended.
Looking at you, AWT.
But yeah, but it's happening out there, and yeah.
Yes, so this is one of the expert options. But most of us, since we are normal industrial developers, we'll just use frameworks and libraries like with everything else we do.
Yeah, there's a couple of details on like, yeah, this is...
Where's my demo? Demo. Yes,
okay.
Fantastic. Push the button. Push the button. We're gonna, now what we see here. We have a project here, and this project is, let me show this, is a Micronaut application. Micronaut is one of the frameworks that supports the native image generation, and they claim so. It's very popular currently as well. I think there is, like the next slot, there is a workshop deep dive into Micronaut.
Yes, and there's also one into Quarkus, by the way, so you will have to make a choice.
Right, so
in the afternoon, there is a Quarkus workshop and a Micronaut workshop. And both of them will mention GraalVM, at least they will mention the functionality of GraalVM and how they can do a native image with it. Right.
So my Micronaut sample application. And it shows that because it's a framework, they say that they work with native images, which means that I can start with a project that already is being successfully compiled ahead of time into the native image, which means I will be adding features and I can always maintain this compatibility versus starting with a project that maybe is not yet fully figured out how to do this transformation, and then I will need to go against the obstacles, right? So my Micronaut application is very similar to a Spring application. So what we have here, we have a class application, we can say Micronaut run it, and we have a controller that binds to the URL, and it has a service. It has a service that will be queried when we hit the random URL here, and this service will give us a random quote. The quotes were taken from a permissive GitHub repository, and they are hopefully inspirational and wise. I originally was building an excuse generator, right? The Jira was down, and my code is compiling, and it works on my machine. But then I figured out the quotes and inspirational wisdom is always better. Right, so it's a simple web application, right? What I can do, I can have my application here, right? You can see this. If I do which Java, just to see, I'm using, oh no, this is the wrong tab. Which Java here? Which Java? Right, I'm using the GraalVM 19.2.0.1, which is not the latest released GraalVM, but it works for our things. And I will build a native image, and I will run my application. So first of all, I can do Gradle. It's a normal application. It uses Gradle, right, as a build tool. How many of you use Gradle? How many of you use Maven? How many of you have heard of a build tool called MX? This is what we use to build GraalVM. Yes, Maven won. If you were watching online, Maven won, but there were very many people using Gradle. So Gradle is a build tool. We need to run the command. I will not run this command, but I will show you the command that we will run. Build native image, right? We will run the Gradle, we'll say clean assemble, and we will get the jar files. Then to build the native image, we'll take the jar files and we'll feed them into the native image utility, providing other options which were necessary, right? So what I can do now, I can do Java, my normal Java, and you saw my which Java was pointing to my Java from the GraalVM distribution, and I can do Java minus jar, build libs, what? Star all, what? Jar. Yes, right? I can start my Micronaut application, and it's gonna start. And it says the startup was completed in 2 seconds, 1.7 seconds, and I can access my service at localhost 8080. Let's go check it out, right? Localhost 8080, what we had? We had quotes, we had random. We have a quote, right? We have another quote, we have another quote, right? Now, currently, our application here is running and is serving us quotes. The exact text is not important, right? What's a good one? Right, too obvious to be true. Excellent, perfect. Right, so what we do here, this is important. This is not a trivial application. It's an application that is using a beam that we are converting into a JSON file, right? So here in the web, it's JSON. Here is the, yeah, I will close this other demo thing, right? File, open, recent. Where did you go? Right, here, right? So here is an object, there is a JSON. How it happens, nobody knows. Actually, there is a JSON converter supported by Micronaut. We put this annotation introspected, and Micronaut is using the annotation processors to generate very many data at compile time while you compile your application into jar files, right? So it does a lot at this step, and that's why the startup times of the Micronaut applications tend to be better on the JVM, and that's why it's a little bit more maybe easier to be transformed into supporting native image, because they do a lot of things at the compile time, right, rather than after it starts, right? So we just do, it's a normal Java application, right? So what I can do now, it's running here. What I can also do, this is very interesting, right? I have my application here. Wait, where is it? Right, quotes app here. I have my quotes app here, and it's the application that was built by this build native image thing, right? So we fed native image with our jar files, and we used some embedded configuration, right? Our configuration was here within our jar files, right? So the config to help native image can be put inside the jar files, right? And it says that our names will be this, and we will include the login configuration, and this is the main class, right? The necessary parts. So Micronaut takes care of that for you. You can specify. It's not hard to write this out by hand. We are, after all, developers. We are paid to do things like this, type text into terminals, to run applications, right? So what I can do now, my quotes application is 67 megabytes large, a little bit larger than I expected. But what it does, quotes app, if I run it, it's supposed to be very quick. Let's not run it. Let's run it again. It starts up in 23 milliseconds, right? And you can see that the actual service is running further. I'm hitting the same URL, and my application features the same behavior, showing quotes, which is to be expected because it's the same application just compiled ahead of time to the native image, right? And it starts up really fast. And if I do activity monitor, this is the layman way to assess memory consumption of the applications. If I do quotes app, the memory of my application here, the runtime, and this is my Mac measuring the memory of this runtime memory. It's not the heap, like it's everything, right? Because the Mac doesn't care if it's a heap or off-heap memory of my application. It's 15 megabytes. 15 megabytes. I think the smallest instance on the cloud that you can get could be like 120. So it's very impressive. For the Java applications specifically, 15 megabytes of runtime memory consumption is excellent. We can do more.
I think we can get even lower, right? Can you just start it again, the app?
Yeah, and I can do XM.
Yeah, let's just improvise a little bit the demo.
16
make it more fun.
16 megabytes. No, it was 16. Let's do.
No, to do 16 max. That's good. No,
wait, we had 16.
No, put MN and N. Yes.
4 megabytes.
Let's try that. Yes, that's a new space size now. Yes, let's try it.
So okay, it started in a similar fashion. I didn't disable my turbo boost, so there's some variability in the numbers is expected.
It depends on how much.
We are using this here,
yes,
right?
Yes,
done. So activity monitor, it's 12 megabytes.
Well, we cut off some more, right? Yes, yeah. Maybe we can even go lower.
So this is the example of this overfitting the problem, solution for the problem.
I'm just saying,
we can do more.
This
we
is
can
not
do more.
the end of the.
We are the boss. We can do more. So now look, with a very small heap, it takes some performance hit.
No, I don't think so. Just try it again. This is just when it loads.
Yes, it doesn't take the performance hit.
when it loads it from disk. Yeah.
Right, it still works. 2 megabytes. What's the? Who thinks it will be lower than 8 meg?
I don't think so.
I don't know. Like I haven't tried. It's 11, right? 11.
Yeah. So I think I get it. Anyway, all right.
It's a ridiculous small amount of memory.
I think
right?
I've seen some guys configure down to 4, but I think then we also need to put MX as well. And yeah, but anyway,
right. So
good enough for now.
What we would like to address next in this demo is a very important notion of startup versus being ready for doing work. Right? Because so far, we are looking at the numbers, and it's like startup completed in 58 milliseconds. I can do that all day. I can just say that I'm ready to do. I'm not saying that I'm doing that at work, but I can say that I'm ready to do work, and then only actually start doing work when people start pinging me with questions. Right? So what we want to measure not the startup time until we see the log line, but we want to measure one answered request. Right? We want to start the service, we want to hit the URL, we want to see the response, and we want to kill the process. And we want to measure the time for serving one request successfully. Right? Because that is the definition of we are ready to do work. This is what we as users care about. Not actual, like the log line. Log lines are also impressive. Right? So for this, there is a very interesting script device. It's called startup test. What the script does, it runs our command, and then in a while loop, it curls the URL until it gets 200. Right? So it gets 200 means HTTP OK, means the request is served, and it will sleep just a little bit, 20 milliseconds, right? It will sleep a bit, curl again, sleep a bit, curl again, and then it will output how much CPU time total my request was using, right? And then it will kill the application. So let's do this. We can do this. Startup test, and then we do Java -jar build libs, and then what was the jar file? Where was the jar file again? Come on. Stop being ridiculous. Yes, Micronaut. Right. Who thinks how much time it will take? Right. Supposedly it should run in a few seconds. Right. So before it was like.
But let's try it again just to make sure it's fair on both sides.
Yes.
Mm-hmm. Yes.
Let's try it again. Let's try it again. So
just to make sure that it's So
let's take the best result here.
That's a pro.
No, like because it's not a scientific, rigorous benchmarking environment. It's my poor MacBook running Docker and stuff.
Yeah,
right.
That makes sense. It's about 1.4 seconds. I think it's good enough. But CPU time use is interesting here as well. So it's a lot more CPU time used than actually real time used because there's JIT compilation and other processes in parallel. That are like actually using CPU time, which means if you start these things, it's taking CPU time away from other things already running on the machine. Right. This is another important consideration. Yeah.
If we run our
Let's try it again.
Binary, we get lower numbers.
Yeah. It's like 24 milliseconds, and CPU time used only 40 milliseconds.
Right. So what it means, there are no facilities that do not do work. Right? It starts and it's ready to do work, and it only uses your resources when it does
like
work.
100x, right? If you go 40 milliseconds, was what was up there? Yeah, it was like
a couple of seconds.
4 seconds. There's 100x lower CPU cycles used to serve the first request. Right? So that's a lot of CPU cycles you can spend some else.
Right. The most important bit is, of course, about the memory, but CPU reduction is impressive. Right? This is not the end of this amazing demo scenario, because who serves one request? There are only one scenario where you want to serve one request is when you're running as a function as a service. Even then, you probably want to reuse the thing, right? You function as a service, you start your thing, you serve a request, and you kill the thing, right? Which is not just saying anything, but there is an implication that native images, GraalVM native images, could be a really good platform for function as a service implementations. Right, so let's try to serve a few requests, and let's also try to look at how the memory and CPU consumption grows, right, while we serve several requests. So we have another script here, which called plot test. And this is the script that uses the PS record utility that Thomas mentioned before. What we will do, we will start our script, we will start our application, we will sleep until it's ready, right? Then we will curl 3 requests, sleeping 1 second, and then we'll kill ourselves, right? So we will serve 3 requests, and we're going to record the CPU and memory consumption while we're doing this. Sounds reasonable? Excellent. So we're going to do this the same way. We're going to do this the same way. Plot, test, and then we're going to do this Java thing. And this is the Java coming from the GraalVM distribution. So there are no tricks or comparisons or unfair comparisons. This is our Java. So we started something, we served some quotes, and then our plot file is here. Right? What we can see here is that we run for almost 5 seconds, which is normal because we slept like 4 seconds out of that time, right? Because we slept between all the requests. But what is important is that we consumed almost 400 megabytes of RAM for serving 3 requests, and also we used quite a bit of CPU. So you can see there is a lot of red there, which normally would be good for Oracle. But in this case, it shows that the compilation facilities are triggering, right? So at the startup of application, there is a lot of initialization. There is a lot of CPU cycles being used for compilation, right? So let's close this, and let's try the plot graph thing for the quotes app again, right? So now we are doing the same thing for the native image. We start, it attaches, it does sleep, it does sleep, it does sleep, it kills, and it shows us the plot. Here's the plot for the native image. We used 35 megabytes of RAM because we didn't limit it, right? Normally we would limit it, say like 16, because we saw it with 16. But here we didn't limit it. And what also important, we use CPU being used only when it's actually work being done. When there is no work done, where we are sleeping between our curl requests, there is no CPU usage. How amazing is that? No unnecessary work done. The planet is too hot anyway to do unnecessary work. So this is the startup measurements for the native image. And also what is interesting and what also brings us back to that diagram. Remember the peak performance, latency, memory, whatnot, and the diagram. Who remembers that? It was on the slides. Nice. What we can do now, we can apply some load to the applications, right? And we're gonna check the basic numbers like memory consumption, CPU consumption for requests, and we're gonna use that in a very ad hoc manner as well, using a different script. And when I say ad hoc, it's a bash script rather than this is unsound, right? What it does, it triggers the same URL from this local host machine, and then it consumes some data from the PS commands, like for example the resident set size, memory consumption, right? And then it prints how much memory we spent on the serving 1,000 requests, and we do that a number of iterations, right? So again, this is just for the purpose of understanding the performance implications of running the native image versus running the things on the JVM, right? So what was the name of the file? The name was load test, right? Load test.
But put an mx comment minus xmx.
XMX. So we limit our memory.
128 megabytes, I think.
How much?
128. Put 128.
This is Java.
No, it's the heap memory only. We're limiting the heap memory, right?
Right, yes. So, no space, megabyte, and space here, right?
Yes, correct.
Sounds good. So we're limiting the heap because we know that there will be no things on the heap. We're serving requests, right? Quotes. There are like 60 of them. We're going to run this. And this is going to take us a little bit of time because we are running the server and we are applying the load. It will warm up the JIT, right? Because it will run for some time. Come on, my poor machine. Yesterday evening, without external monitor, it was faster.
Well, let's see.
It should print something.
Requests, it should print something. Yeah.
It should print something. Yesterday, it printed something. So it started. Let's see if it works. Yeah, it works. So it should be right. So we see
took
that.
some time.
So we served. So n is an iteration, and we serve 1,000 requests in each iteration, and we record how much CPU time it took us to serve 1,000 requests, RSS, and request for megabyte for
request per megabyte
memory.
second. Yeah, and it's 10,000 requests. I think it's 10,000 per iteration. But the interesting number here is the last one, which is requests per megabyte seconds. Like how many requests could we serve for occupying a certain amount of memory for 1 second? In this case, it's 13 here for Java. And the third column here is the throughput, right? It's requests per CPU seconds. How many requests can I serve for 1 CPU cycle spent, right? Initially, it's pretty low. It's only 754 because I'm using so much CPU cycles for JIT compilation. And then as the application warms up, it goes to higher numbers, right?
Yes.
But let's put native image as the counterpart here.
Let's do this. Quotes up, and we
also
do
put MX, also 128 megabytes is good. Let's
Really?
just configure the same thing.
Right.
You need an M.
New generation.
No. MX, but an M in the end.
Yes, megabyte. Right.
Yes,
Wait.
but now you have...
I need to kill something.
Yes, you need to kill a lot of stuff probably.
Quotes up, kill. Right. Let's do this again. This works. Megabytes, load test, quotes app. Should work. Starts in 31 milliseconds. Good. We see much faster.
We already got the 10,000 requests, right? If you saw in the JVM version, we were waiting like really long for the first 10,000 requests, right? So even for 10,000 requests, it's like a lot better.
Right.
And what you see here as well is like the requests per CPU seconds is lower, so the throughput is here lower on native image.
Because JIT is best.
Because the GraalVM JIT mode is best for throughput, yes. And but the residence size is much lower. We can probably configure it even down on native image. I was here generous in the sense of like giving it a relatively high number. And but that means the request per megabyte second is like it's 9x better than on the JIT mode.
Which means you can scale the native image application much better, right? So here we used...
this is what you usually pay for.
We used 400 megabytes. So we can put 10 native image applications. Well, 8, say, right? 8 native image applications that will use the same memory. 8 native image applications will probably scale better than that one instance we had. And to even pump up the game a little bit more, I used the profile guided optimizations for the native image generation, which is the enterprise GraalVM enterprise feature. But what it does, you run your Java application and you record the profile data using some command line parameters, and then you use that profile data to generate a better native image, right? So, and I can do this again. I think PGO. Woo! Right? I expect this throughput here will be better.
Let's see.
I hope. Probably not. Something broke.
Wait.
No, something broke. It was faster before. Scratch that. You didn't see that. I didn't show you how I generated this image. This is incorrect.
This is probably fine. Let's see.
No, something is wrong. Yeah, it's just like it's incorrect.
Yeah, no, it's fine. This is to do with your network interface being in a weird state. But yeah.
I don't think this is correct. No, this is not correct. This is not what I saw yesterday.
Yeah, okay. So request for CPU seconds actually doesn't go up here, yeah.
Doesn't go up.
But
so to see this demo in full potential, please welcome my session on GraalVM native images specifically on Wednesday. Right.
But
scratch that. Sometimes
PGO can give you advantages, but not always. And but we are generally working on trying to get the throughput to the same levels, also with
JIT.
As with the JIT, yeah. Because we notice there's a few things that are different in the runtime, and these are reasons why our ahead of time compile mode currently has worse throughput. but we are fixing those reasons. I mean, some of them might be garbage collection related, so the garbage collector can play a factor in throughput, but others are related just to the general runtime system we're using there. We haven't implemented a couple optimizations that we have to do. All right, cool. So, interesting. Yeah. So let's
right. Let's go
back to the slides, or
yes, we can go back to the slides. Interesting. Well, requests per megabyte per second go up.
Before we go back to the slides, I have fixed my demo in the meantime. It's good to have two speakers.
Let me fix this.
So yeah, exactly. So now it's your turn, Oleg. So I've changed my demo a little bit because GMH is sometimes a little funny because it gives a couple hints to the virtual machine, and it's actually only really suitable to be used for hotspot and compilers that are kind of make sure they really respect those hints. I've modified the demo here a little bit by putting the result value into a volatile int static field, which in most cases should make sure the compiler is not cheating. And in this scenario, I've just run it here before, so you can't believe me. But in this scenario, this is JDK 13 here. So the score is a lot lower now because the volatile field store is preventing some optimizations on Intel hardware that would otherwise occur. But so the abstracted version is here only half the speed of the raw version, and the raw version is 111. This is on JDK 13 hotspot C2. And we have up here, we have the run for the OpenG9, Eclipse OpenG9 on JDK 8 here, with so the peak performance on the raw version is the same with 111, but the peak performance on the abstracted version is about 50% below hotspot at 40, and above a little bit further up, this is the where is the stuff? This is the let's just run. Yeah, here's the GraalVM Community Edition, where the abstracted and raw versions are both 111. So that's just because in the other scenario I showed before, the GMH had a there was a GMH bug in the sense that OpenG9 wasn't respecting some of the GMH flags. But this is a general reminder. I think some of you know this disclaimer of Alexei Shipelev at the beginning of GMH. Kind of be very careful with what you measure. It's actually what you think you measure. Because one has to be, specifically if you're not using GMH, it's even worse. One has to be very careful about the benchmark setup, reproducibility, and making sure that what is measured is actually what is. Yeah. It's
best to measure your actual workloads.
Yeah,
in simple terms.
But even for your actual workloads, it can be relevant on what type of setup you make in terms of what you measure. Right? So one of the things that's often more interesting to measure than the time, the wall clock time, is CPU time. This is why we often measure CPU time here, CPU cycles used by the process, because this has a lower variability. Because on an application that uses network, then maybe there is something it goes back to the OS because of the network interface, and there could be some variability there, also on the kernel OS side. But if you measure the CPU cycles of your process that is spent on user mode on your process, you're likely going to have less variability in measurements. All right, so let's go back to slides.
Just a few slides, just finishing notes for the native image section, right? Are they showing up? Mm-hmm. Yes, right. So it's really good for serving like a small number of requests. The benefits are just the comparison is not like it doesn't even feel fair, right?
Yeah. So here is another version of this PS record graphs that record over time the CPU consumption and the memory consumption. And as you can see here in this scenario, at the beginning on the JIT mode, you have a lot of CPU consumption for the just-in-time compilation. But also after a certain number of requests, there could always be a spike in CPU consumption, because maybe another method suddenly got hot in your program, and that triggers more JIT compilation. So this adds to unpredictability of results, specifically also at the first few requests that are served, right? Which can add to your tail latencies.
Right. So we looked at a couple of command line flags. There are actually a lot of flags, right, that you can tune and turn about configuring your native image, right? Both less at runtime, more at the generation step, but still the most important are, since the memory footprint improvements are probably the most important ones, the most important are to tune that, and you just do that by limiting the memory, literally, right? So either the maximum memory or the new generation size, which is specifically important to the person who was asking that question about allocating tons of objects quickly that will quickly go away.
Right. Yeah. And so the default values for these things is max memory is currently default infinite, so it tries to allocate as much as there is available, and new generation side is defaulting to 256 megabytes. Both of these values are not ideal if you want to tune for low footprint.
Yes. So if you just start the native image of your application, you measure the memory and you apply load, and your application generates data again and again and again, like for something, right? It will just consume all the memory.
Yeah.
So
because this is a typical trade-off of throughput versus footprint. So if you configure small memory, it means more garbage collection happening, more time spent in garbage collection, which might mean a slightly lower throughput. Sorry. But on the other hand, and that's why we by default kind of just use the memory that's available.
It's reasonable. It's a resource given to us,
but
right?
there's like a sweet spot in there where like you shouldn't reduce it so much that you see a severe throughput hit. But basically, the default values are far too high to optimize for requests per megabyte second. This is why our load script is basically measuring requests per megabyte second, so you can then optimize for this metric.
The dense memory usage, right? So you can scale your application as you would do.
Yeah, but it also depends on throughput, because if the throughput drops, you will serve less requests on 1 second. And that means less requests per memory second. It's a combination of the two.
It's a trade-off. Remember the diagram? There are trade-offs there, right? So for the best usage experience, probably currently, you want to use one of the frameworks that supports that. Is either Micronaut, Helen, Quarkus, or the upcoming Spring support, which everyone is waiting for and a lot of people are working on. Like at least some people are working on it. People are actively working on it, and there is active progress being made.
Yes, and there will be some more progress being made at this conference.
Yes.
Because we will be able to meet with the guys again.
Right. So if you use those frameworks, of course you will see some variability in results, right? Because it's natural. They're different, right? You're running maybe similar application, but because of the framework is different, they are a little bit different, right? So, however, you will get very similar results and very similar performance gains, both in startup and memory usage, regarding of the framework usage, right? So the startup time on the GraalVM native image drops to milliseconds, right? And the memory usage drops to like a few dozen megabytes, right? 40, 60.
Yeah, and what's important is like this is not a comparison between frameworks here. Like you can configure them probably differently, and I think Micronaut actually reduced their footprint recently quite a bit. Like for all of the frameworks, native image is the key component that gives the better startup and the better footprint. Like some of the frameworks sometimes talk about how they are so good in startup and footprint, but the key component that makes those frameworks better is the GraalVM native image component.
Yes, they also could be different, like their startup and memory usage could be different for running on the JVM as well, right? But the ridiculously good numbers come from using the native image.
Yeah. And also note, like there's also this thing where like people say, oh yeah, there is AOT efforts in various other virtual machines. Like Hotspot has an AOT effort, OpenGenite has an AOT effort. Those AOT efforts first usually reduce the startup time, maybe by 40%, 50% if you're lucky, not by 40x. So they have a lot less reduction in startup time, and they don't give you any reduction in memory footprint.
I mean, they can give you perceived reduction, but it's actually configurable.
So the real deal in terms of getting to a low memory usage, getting to a fast startup is really native image. And yeah, of course, it comes with these trade-offs that like we currently cannot support kind of the arbitrary application to be run in this specific low footprint mode. But these trade-offs enable us to get really to the bare metal performance.
Right. And it makes the, there is a question.
Is this memory footprint increasing during runtime, or it keeps this low?
Mm-hmm. So this will keep this low, specifically if you configure it. So if you put no configuration on native image at all, then it will just grow the usage. So it might grow, but if you put an MX, you can configure all of these frameworks in a way that you will get this memory usage like for serving the requests. I mean, of course, if your application itself is like allocating a lot of data structures in some caches or whatnot, right? That's a different story. But if you configure it, it will stay that way, yes. And that's kind of important. Some of the guys who give demos on GraalVM and other frameworks are only showing like the first two requests. And that's not appropriate. You can show the first. We showed here like 100,000 requests being served, but in order to keep the memory footprint low, we had to configure it because otherwise the default would be like, oh well, there's memory available, let's just use it.
Which is, why is it so, a little bit, just for the context? If you're running in constrained environment, like in a Docker container, it actually makes sense to consume all the memory available for that particular Docker container, right? Because you probably configure memory on the like higher infrastructure level, like for your Kubernetes pod or like Docker container, right? So like everything within that is fair game, right? But if you're running on your powerful machine or in a powerful like not constrained environment, then consuming all memory may be not the best idea.
Yeah, and for the memory consumption, there's these two flags that are important, MX and MN, right? These are the two tuning flags here.
And print GC.
And the new generation size is kind of important. You should set it in a way where like most of the temporary allocated data structures of the application fit into that new generation size. You can put the maximum memory on a relatively conservative value. That doesn't matter much because the old generation might not grow anyway because it's just the data structures that are long-lived. But if you don't configure the new generation size appropriately, then your application is going to use at least this 256 megabytes because it will grow the new generation size to this point, and it will just allocate everything in this space before ever doing a garbage collection. We would usually recommend just testing your application on a couple of these values because it depends on allocation rate and what you want to achieve to get the absolute best results. But for one of these Micronaut examples, a new generation size of 16 megabytes is plenty enough. And then you can put max memory at 128 or something, but you will actually not use that. Yeah.
Well, it depends heavily on the workload, right? How much data you actually produce while serving a request. Do you keep that data in memory for caches or other intermediate calculations, or are you just hitting like a Kafka and then process a message? Like you probably end up with like dozens of objects and they will die with the like request-based applications have natural scope, right? So the new generation is much more important than
and what you would prefer in terms of application architecture, right, is to scale via multiple processes. Often, like in Java, people are historically trying to scale via multiple threads. And the reason for that is that the JVM is so heavyweight in terms of additional memory requirements that people try to run as much as possible on the same JVM process. So you scale by having multiple threads. With native image, the preferred way to scale is by scaling via multiple processes. And this has various advantages. One advantage is robustness, because if one of a process goes down, the others are not going down with it. This has advantage in terms of less GC coupling. If there's full garbage collection, only that process is going to be garbage collected. So you naturally have like different heap sequences for your application. And the other advantage is that it just scales better and works better in a Kubernetes environment where you just like spawn up and down the processes. So it's really trying to scale via multi-process architecture instead of scaling via multi-thread architecture. And some of the applications that might have performance problems on native image are because they are not designed for this type of process scaling, but they want to scale via multiple threads and have like 64 gigabyte of heap and so on. So we really think that here native image is tuned for multi-process scaling, lightweight processes. Start many of them. Could be Lambda functions, could also be microservices.
Yeah, it scales like some other languages which you might think of rewriting your Java applications in for better cloud friendliness, cloud nativeness, right?
Yeah, all right. So we have Bruno Borges from Microsoft, his Microsoft product lead for Java nowadays. So naturally he likes Java.
Yes, and as an influencer in the ecosystem, Bruno thinks that GraalVM native images are clearly a thing to
get to a low footprint thing. To both compared to both Node.js and Go, right? So effectively, like you get a similar characteristic like a Go binary, and also a similar characteristic like a Node.js application. You get actually better characteristic than Node.js application because Node.js applications still need to dynamically load and compile JavaScript quite a bit. And also they do it with a low footprint. It's not zero footprint.
Right. Perfect.
So yeah.
What we would like to have native image, we would like to improve the peak throughput to the limits of the JIT, or at least some JITs. We would like to improve the latency results, right? To do garbage collection, and stuff is in the works for that.
Yeah. So on the latency question, if you configure a relatively small heap, then the latency is still good on native image, because even if you do full GC from time to time, it doesn't add so much to your latency. But if you have a mid-sized or larger heap, then the current garbage collector native image is not designed for the best latency.
Small heaps.
And so we're working here on a project to create a new low latency garbage collector for native image. We hope to be in preview form in 3 months from now, early next year with 20.0. Release of GraalVM to have this as a preview. And we are working on peak throughput performance improvements to make sure that the peak throughput is the same. It shouldn't be too hard. Maybe some will require PGO, like profile-guided optimizations. But even without profile-guided optimizations, it should be possible to reach the same peak throughput. And for certain frameworks and stacks, it is already the same. So we tested the Quarkus stack on peak throughput, and it was practically equivalent. But that's because they use Netty, and Netty uses unsafe, and so has special optimizations that are very good for us to be also done on native image.
Right. So there will be another session on the native image, with a little bit more hands-on walkthrough about how building then works and how you would deal with the code. So you're welcome. That's on Wednesday. But let's go into the polyglot and embeddability.
The third part, yes. Third part of the you still can handle something GraalVM related. All right. So it wasn't the question. It was just the
yeah. You're not going anywhere.
So in order to refresh things a little bit, we are no longer talking about native image. We are no longer talking about Java. We are now talking about polyglot, and which is one of the, I think in the future, I think currently a little bit unrecognized capability of GraalVM. I think in the future it will become more and more important. And this talk will this part of the talk will try to encourage it.
Spark some interest. Like, I feel like polyglot as a term was a little bit tainted by the predecessors, right? The JVM had to be like the polyglot virtual machine. The .NET virtual machine had to be the polyglot virtual machine. But it's always there are limitations because they're just designed for languages which look like their original languages.
Right. Yeah. So the like when we talk polyglot in GraalVM, or when we implement these languages, we really try to implement them in a way where like we reach the full peak performance and full language compatibility for these languages. We did a recent Twitter poll just about a week ago. Everybody who participated, thank you. I got more than 1,000 votes, and we asked like which of the following GraalVM languages are you most interested in? And these were the results. So we got Python actually as number one. We do have a Python implementation on GraalVM. It's a little bit experimental at the moment, but we're actually prioritizing Python quite a bit to run Python on GraalVM. The other language that got high votes is JavaScript. JavaScript on GraalVM is very mature at the moment. It's ready for production. You can use it in the context of your JVM-based application, or you can also use it just to run Node.js.
I think we've heard of both being used in production, but not publicly people coming and speaking yet, at least in English.
Right. Yeah. And so this is some technical details, but like maybe so this is for the Node.js running on GraalVM.
Right.
So when we run Node.js on GraalVM, we actually run it in a way where we are linking GraalVM together with the Node.js platform. So this is really linked in. And it means we are 100% compatible with Node.js, but you can run suddenly all of these other languages in the context of your Node.js application. So you can run Java, you can run Ruby or Python in the context of your Node.js application. Our JavaScript implementation is super complete. There is something that's called Kangax table, which checks the completeness of JavaScript implementations. And this is on the latest ECMAScript standard. The JavaScript you run on GraalVM is practically the same completeness as any other browser. It's actually much better than the Edge browser.
It's better than Node. I think there are some tests behind some flags.
There are some flags that are not enabled here. It's kind of the same level here. But it's just to show you, like, we're really up to date with the latest features. This is the latest and greatest JavaScript. There's no compromise here, right? So you can actually check. We have something that we call a module compatibility table on our website, where you can put in the name of a JavaScript module or Ruby module or R module, and it will tell you whether we have been able to run tests on this module. You can also upload a JSON dependency file, a Ruby gem file,
and we'll check
it will check all dependencies of this file, and I will give you a first hint whether running this type of application on GraalVM can make sense for you. So why would you want to do that? Why would you want to run JavaScript on GraalVM? There's a couple advantages and some disadvantages. The advantage is currently that you can have Java interpretability, and this is interesting for some scenarios where maybe in your company you have some Java library that you really need to use for authentication or other base services, but you really want to do a Node.js app. And we enable you to do that because you can access any Java library from your JavaScript code. You can access other languages, Python, Ruby, R, of course. The other advantage here is you can run as part of the JVM mode of GraalVM. You can run suddenly your Node.js application with the garbage collectors of Hotspot, meaning very large heaps, and very server-side type of like workloads would run better in this setup. Because Node.js is combined with V8, and V8 is mainly optimized for a browser setting, for a client-side setting, which is not always the best for large heap configuration. We have currently two disadvantages. One is we have a longer startup time than V8. We are working on improving that, but we currently need longer to compile the JavaScript when we dynamically compile it. And we have a higher memory footprint than V8 when we compile the JavaScript. This is because V8 specifically is designed for those two things a lot. In terms of peak performance, we're approximately in the same ballpark. We have this is like showing their own benchmark suite, which is the Octane, the V8 Octane benchmark suite. And we have some benchmarks that are a little faster, some are a little slower. but it's the same ballpark. It's really not a second class JavaScript. It's the first class JavaScript, fully compatible and performant. And one of the things you can do, one of the use cases for you as well, is to embed JavaScript into your Java application. One area where this is interesting is the area where you want to customize your cloud application. One of the largest customers for our JavaScript implementation is an internal customer, which is the NetSuite product at Oracle. The NetSuite product is an ERP product, and they allow their customers to create scripts that will run on their servers. And those scripts are created in JavaScript and then run within their servers. So what we offer here with GraalVM specifically is to do some type of sandboxed execution of the JavaScript in the context of your Java application. So you can create a new context here, and then you execute JavaScript in the context of your JavaScript application. You can make your Java application customizable. The other thing that is more related to some of the research aspects of GraalVM is that one of the things it allows us to do is, like, GraalVM has this built-in way where you can, where every object that it works with can have a completely different logical layout compared to its physical layout. My example use case here is here on GraalVM, an example script where you execute some JavaScript, and then you give this JavaScript an array data structure. But this array data structure is never physically allocated. It is only available as a computation. So in terms of physical layout, it's like it occupies very little memory, but you can work with it as if it would be a JavaScript array. We use this same technique, by the way, when we are moving objects from, let's say, Java to JavaScript or from Ruby to JavaScript. Our approach is to never change the physical layout of the object to avoid any type of copying, and then to only convert the objects and values at the latest possible point in time, only when they are actually used in a certain computation. So this is for JavaScript. We not just do JavaScript, we also do R. R is an implementation of GNU-R on GraalVM. We call it FastR. And it leverages the same infrastructure, same GraalVM compiler, same interoperability. In terms of compatibility with GNU-R, we have some core packages that are fully working. Again, one of the packages here is RJava, which is the compatibility layer between R and Java. This is also the layer that we specifically make faster. So if you have a Java application and you want to interoperate with an R application because you want to do a plot or you want to do some scientific computation that is better done in R, you can do it on GraalVM within the same process, with the same compiler, with the same infrastructure.
Both way. So can the R plot access data in Java?
Yes, this works. Does this work both ways? Yes, this works both ways. The R plot can also access data in Java and the other way around. In all of this scenario, it works both ways. Also, the JavaScript can access the Java can access the JavaScript. And so, like, the alternative to this actually would be to like serialize the data, start an R process, give the data to the R process. There's some communication overhead in that. But in addition to the communication overhead, there is a lot of manageability overhead to it, because you need to manage the processes that you spawn up and down, configure their memory requirements, etc. And with GraalVM, you can do all of this in the same process with the same compiler infrastructure, with the same runtime. This is one of the examples we do as well here, where our faster implementation is not always 100% compatible, so maybe some of the startup of your R application is not running on it, but then you might have some core computation of your R application that you want to offload to FastR because it's faster. So in such a scenario, what we offer is we have a FastR cluster package, which is an R package that allows you from your traditional GNU-R to call out to FastR for a specific computation. And here we have an example R program where we call out to R to do a plot and then get it back, and then display it here in the standard R editor, which is RStudio. So this is for R. Then Python. So Python performance is comparable with PyPy, which is the fastest alternative for Python. PyPy is also a JIT, has also a JIT compiler. What it shows here is that for pure Python code, the performance improvement can be really huge. So we have here micro benchmarks where the performance improvement on pure Python code is in the 50x, 60x ranges. And but for shootout benchmarks, this is also 10x. So, but this is all pure Python code. When you use Python mainly to talk to native libraries like NumPy or SciPy, then you won't see those speedups because most of the code that's running is actually C code. And if you have pure Python code, then it runs very well. Python supports the same polyglot capabilities as the other languages. This looks similar in all languages. Here I have a Python example. You can evaluate from Python, here for example, an R program. This can be interesting if you kind of migrate an application from R to Python, but there is like these two libraries that you still have to use for some reason. Then you can use this from your Python. You can do this here for any language, any GraalVM language. You can execute here not just R, but like JavaScript, etc. So for Python, we are a little bit not so far ahead like for the other languages because we started later. So the pip installer is not available yet, but we do support basic NumPy and SciPy examples, which is also the main thing that we're working on. All right, and so this is now a polyglot demo that you want to show you?
Yeah, I can show it. So now we support a bunch of languages, right? And they are, for any particular person, they could be of different levels of interest. So how many of you are interested in Python? Yay! JavaScript? Not bad. R. I salute you, one brave person. Ruby. How many of you run code written in native language? C, C++, Rust? Nice.
Right, so Python and JavaScript. That's
Python and JavaScript. Well, expected. Right, we turn back to our application here. And I'm going to show you a couple of demos. So first, I know that there is, since we talk about polyglot, and naturally, GraalVM is the virtual machine that specifically gives a lot of benefits to your Java workloads. And one of the polyglot aspects of GraalVM is that you now can share your Java libraries, which probably you have most of the libraries that you have and deal with are Java libraries. Now you can share that to people writing other applications. For example, there is an awesome Java library called test containers, right? It's an application, it's a library to manage Docker containers programmatically. You would use that from your, say, unit tests to kind of create the Docker environment programmatically. I'm going to show you how to use that from a node.js application. Stand back. Right, so what we're going to run? We're going to run this file called application index.js. It's a node.js application. And it will use GraalVM's interop with Java to access the library and the classes from the test containers library. Right? We will need, when we run this, we will need to ensure that the Java classes are on the class path, that our process knows where to find those classes. But then we can use the library from our JavaScript code as normally, like as they would be JavaScript objects. So we would access the class generic container. We would create a new generic container from an Nginx image, and we will run it, and we will expose the ports, and we will print something out to the console. We have our Docker running here, and I'm just gonna run it like this, right? So I will start my node, and I will do which node to show you node tricks. This is my node coming from my GraalVM implementation. The thing that Thomas showed, right? It will start the node with normal node, which will do the normal node things, and then it will link in the GraalVM with all its capabilities. We're going to run it on the JVM to ensure interoperability with the JVM, right? Because the alternative would be to run it with all the interpreters compiled ahead of time into native images, and then there will be no JVM. We'll run it on JVM, we'll give it a class pass saying that, oh, this is my jar file that contains all my test containers classes, and we'll run this application, right? And as a result, it will load a little bit, quite a bit. It will load everything. It will load the JVM. It will load the application, and it will start. I hope it will start. Yes, it checks Docker. I have memory, and it checks and it prints us the URL. And if we access this URL, we should see, what should we see? We should see the Nginx. Welcome to Nginx, the most spectacular demo ever, right? What just we did, we took that Java library, which is popular. I know that it's popular because there is the deep dive on test containers happening in parallel, right? So we took a Java library that we use and we offered it to people who write Node.js applications. First, they can benefit from managing the test containers programmatically from tests when they write tests. And second, they also can enjoy all our null pointer exceptions now in their Node.js applications. Because I don't think they by default have that. And this is not something that we would like to be just specifically for us. Right, so it's a small application. We used Java from Node.js, not the most ridiculous example of the polyglotness that we can do. What we can do more, we can do this function graph demo application, which is also, let me check, which is also a Node.js application, but it will use more polyglot facilities. So, and it will do that in a little bit more idiomatic way. So we would use, it's an application, it will like bind the port somewhere. Let me actually run this. But run, no, what do I do? What do you do? Node ---- polyglot. What? Node JVM ---- polyglot. Why there is no thing? Server.js, right? Boom, done. It will start and we'll look at the code while it starts. So we will use the validator for some code written in Ruby. We will use some plotting functions from R, and we will host our app in Node.js. And it started here, and it's listening, and I'm gonna localhost 8080, and we can do functions here. What? X, draw. It will load the R facilities, and it will give us a graph. We can do more complex.
Cosinus of yes.
We can do more complex graphs. This is a sine.
Beautiful.
We can just divide that by x, for example, and we get this shape here. Mature audience, I see. Right, but what is happening currently? What is happening is that our Node application running and is using R and is using Ruby for the things. How we can see that is doing that? We can give the -- inspect, and we're getting into the tooling section a little bit. So with the -- inspect, what we can do, we will enable the debugger integration for our application. So here, what we see the source code of our application here in the Chrome debugger, right? The thing that was designed to debug JavaScript, and we can put some breakpoints here, and we'll also see other classes here as well. We'll put some breakpoints in those as well, because why not, right? We're polyglot runtime, we can do things, and we're gonna hit this again, and we do the same laugh-inducing thing, and we hit the breakpoint. Normal thing, we are in the JavaScript code, right? We see the values and everything, but what we can also do, we will get the validator, we can go and debug our, what was this? Ruby code. We can debug our Ruby inside our Chrome debugger.
Yes, if only the Chrome team would know about that, right?
I think they know. I think I went to a JavaScript conference once and I showed that, and there were people specifically from the dev tools. What more we can do here, this is actually even more spectacular. Remember, we started our application with the JVM interop, right? So here, I think this works. Java type. we will access. I've heard until recently there were no big integer numbers in JavaScript. There are now there currently, but what we can do things like this, and we can access Java type, Java class, Java mass big integer from our console of our Chrome debugger, and we can get our large number arithmetics in our console here.
That's a new Java console.
Yes.
Java shell.
This is the REPL, available in Java 8-based distribution.
Cool. Amazing.
So yeah, quite spectacular. So you can debug that. You can. The thing is, the important bit here is to understand that the languages go through the same facilities on the GraalVM side, right? Not the JVM languages currently. They just go through compiler. But Ruby, R, and JavaScript and the native languages compiled through LLVM, they go through the same infrastructure, which means that the tools can integrate with GraalVM and support those languages out of the box, right? So you don't need to figure out, how to do specific things for Ruby. For example, right, the debugger, or for example, what we can do here is we can run JVM, which is the Visual VM, the tool to do memory analysis and check the performance characteristics of Java applications, right? And we can see a certain GraalVM process running on my machine here currently, and we can monitor it. And we go and let's undo debugger. How do I skip all breakpoints? Pause and deactivate breakpoints, right? And we'll do this.
You need to still continue. Continue.
I need to continue. Yes, continue to draw. No? Are we stuck?
No, I think we're good.
I think we're stuck.
Yeah, and that's good. It's good.
Right? Let's multiply by x. Let's do
better.
Excellent, right? So, and what we can see here, we can see that we're monitoring our Node.js application inside our Visual VM. How amazing is that?
Yes,
what we can do, we can do more.
Snapshot, maybe.
We can do a heap dump of our Node.js application.
Yes.
Heap dump, right? And this heap dump will, what will it do? It will show us the summary of things, like this is normal thing, but also we can check the JavaScript heap of our application and see what JavaScript objects are taking the most space. It's going to compute for a little bit, but it should show things. Or we can do R heap or Ruby heap, because our Visual VM knows. So this is the Visual VM bundled with the GraalVM distribution, right? So it is GraalVM aware. So it has those facilities to recognize the GraalVM polyglot things. It's computing. Let's not go. What I wanted to show, it also comes with a very interesting, cool thing here, just to show off. There is an R console in Visual VM, right? So when you get the heap dump, right, you can write a certain script to analyze that heap dump. Well, guess what? Now you can write the script in R. So if you have a data scientist with a little bit of free time, you can maybe employ them to write scripts to analyze your
heap dumps.
Heap dumps.
Yeah. This is another case of where we embedded GraalVM in there, and where embedding GraalVM in your application can make sense, because suddenly you have like data science capabilities.
And this is actually not very many people were interested here in R, but I think the most publicly outspoken deployments of GraalVM, which use the polyglot facilities, are actually specifically doing the R for data science and interoperating with their Scala applications. Anyone from the Netherlands? So the company that is doing that is Dutch police, right? The Dutch police, the law enforcement facility, right? And there was a session at JavaZone, and there was recently a session, I think at JFall somewhere, about from Nathan, about how they do that and their lessons learned and how they are successfully using data science. And everyone is happy. Data scientists are doing R. Data scientists are doing what data scientists want to do. They do data science, right? And their developers do what they want. So instead of managing Docker containers for those R deployments, they actually write their Scala application and produce business value. So excellent collaboration going on. Well done, Dutch police. Right, so there are tools, right? So the tools integrate with the GraalVM, and get support for all the languages. We get, among other tools, we get the profiler, so both tracer and the sampler, so you can figure out the performance of particular bits of your code in those languages. Profiler, heap viewer, debugger. Yeah, the normal developer tools, right?
Yes.
The tools that you use every day. So when you're going to the polyglot application, you don't actually have to be crippled in the process of how you do things. Another company I know, quite a large deployment, they do the server-side React rendering for their applications. And they didn't go with the normal node.js server-side rendering because they have a large Java application. So they didn't want to send data back and forth on the back end from Java to Node to just render React. So they're running the React rendering inside the Java, and they save on the interoperability, and they use the debugger, and especially extremely happy about the debugger capabilities because their front-end people would like to use a debugger, and they cannot if it's not available. So all good, all good, all good.
I think it's good.
Yeah, we should go back.
Maybe let's see if it computed this heap dump thing, or we need to submit a bug report to the team.
One.
No, go to the heap dump on the right.
Yeah, here.
Oh no, on the This,
no,
yes.
this is it. No.
Yes. Did it compute? Oh, not yet. All right. That's a bug report.
I think the thing
right,
is, the main takeaway is that I need a better laptop.
Yes, certainly. I see where you're going there. All right, cool.
Right. So yes, I have more demos for the polyglot, but they're less impressive that we saw currently. Go.
Right.
We have 16 minutes.
Yes. So this is just a screenshot from GraalVM, just showing a polyglot stack trace. We can have here stack trace in GraalVM with multiple languages, and we have.
This is the actual heap dump computed.
This is the heap dump computed. This is what it should show here. Here in this case are objects instead of JavaScript objects or Java objects. All right. One other more prominent project that is using us is Vertex, and Vertex has a special sub-project that is called ES4X. This project is about combining our JavaScript engine with the Vertex platform. And it's currently one of the most performant web frameworks out there based on the Tech Empower benchmarks. There is, you can read more on that on the Vertex website. And the lead developer, Paulo Lopez, is very great.
Here.
Yeah, he might be here. Maybe
Paula in the room? No. Probably just.
No, I just want to shout out. Very great to work with Paulo, and he's one of the guys here embedding GraalVM in the platform as well. All right, we do support other platforms via an LLVM backend for native image, and one of the companies we are working with there, and this guy is for sure here, John Voss from Kluon. HQ, who are building cross-platform tools with GraalVM native image for mobile platforms, including iOS, Android, and Windows. So this is still work in progress, but you have some demos here where I have, for example, Scala code running on the iOS device. All right, cool. Let's go to the summary, because we have 15 minutes left, so let's summarize. Key performance takeaways. We haven't talked so much about practical tips, but in this scenario, I want one practical tip that you should kind of get away home with. It's some key performance takeaways. One is, I think what's important is actually writing small methods in your code. The reason for that is that the JIT compiler can inline methods very easily, but the JIT compiler has a very hard time outlining methods. So it either inlines the full method or nothing. So if you write small methods, you give the JIT compiler a lot of choice. If you write big methods, you don't do that. Second point is local allocations are free, global data structures are expensive. So when you do allocations locally, then often the just-in-time compiler can remove them completely. If you do them globally, these are the data structures you should optimize, meaning the ones that you cache are the ones that are caching issue. So point here is don't hand optimize too much before you started the compiler graph, because you might actually do some optimization that the compiler has to undo again. Like in this case in the JDK, the optimization for converting double to raw integer bits. And for best throughput, use GraalVM JIT. For best startup and footprint, use the GraalVM AOT. Top 3 misconceptions about GraalVM. We were talking about this already a little bit. And yes, so assertion GraalVM does not support reflection and can only run a subset of Java. That's false. That's completely false in many ways. First of all, GraalVM has a JIT mode that runs everything just as a drop-in replacement by putting you put the Java home to the GraalVM home directory, you run GraalVM. The second point is that like here, even in AOT mode, we support everything by a fallback image, and we also certainly support reflection. Is this making a mess somehow? Maybe Oleg, you take over for...
Yes, so maybe this one you should take on.
Oh no, okay. So GraalVM is a competition to hotspot technology. That's false as well, because GraalVM incorporates hotspot technology. So when we are shipping GraalVM, we actually ship hotspot as well with it. So GraalVM is an add-on to hotspot technology. We incorporate it. And the GraalVM JIT mode is based on the hotspot technology. The GraalVM ahead of time compile mode does not use hotspot technology, except during the image building process, in which we also run on top of hotspot technology. All right, and
this one I can take.
Right.
So GraalVM is just a research project and is nowhere clear to be ready for production. This is clearly false. There are a number of companies who are running GraalVM in production. GraalVM is 100% production ready. GraalVM is a mature project, as Thomas mentioned. The first bits of GraalVM were written like 8 years ago, right? So there are companies running different parts of technology stack in production right now. And there are, what you need to be aware of, there are certain...
There are different parts, right? And that's on this slide here, meaning there is... When we talk about GraalVM, it's really many different things. And this is why usually when you talk about GraalVM, it's good to qualify what part you actually mean. Do you mean GraalVM ahead of time? Do you mean GraalVM JIT? Do you mean GraalVM polyglot, etc.? And when we talk about GraalVM, often, and this is maybe a little bit our fault, we talk about many things and we don't classify very, very specifically what is production ready right now for use in production, what is already in production. What is currently experimental, you could use it in production, but it's kind of a little bit on your own risk. And the third part is what is like more visionary, meaning like we're working on it and it's like you can have a small preview of it, but it's really not something you would recommend running. And currently production ready is of course running Java applications, any JVM-based languages, Scala, Groovy, Kotlin, like we are 100% compatible. We passed the TCK with GraalVM. We verified that. And second thing that is production ready is JavaScript and node.js. We are very confident that it will run your JavaScript application correctly without problems because we have a very high compatibility standard. Native image is production ready, despite what there is various additional disclaimers on it, being early adopter, etc. It is still ready for production use right now, and we encourage production use for native image. And Visual VM as well is also production ready. So what is experimental at the moment? It's kind of, you can use it, but it depends a little bit on your type of application. Is Ruby, R, and the LLVM toolchain that allows us to run static languages. Some people use Ruby and R in production. Shopify recently tweeted that they are using Ruby in production, or certainly working on it. And for their Ruby on Rails stack. And we have R being in production at the Dutch police. So, but it's kind of can run. We are not yet confident enough to say, well, you have an arbitrary R and Ruby program, it will run it correctly. We are not sure. It's kind of your own risk to test it out. And there's a couple visionary parts that we're currently working on. One is Python. So we are accelerating the Python support at the moment. One is a Visual Studio Code plugin, We are working on adding a plugin to Visual Studio Code that allows you to use the polyglot capabilities of GraalVM better and also gives more tooling support for the native image parts of GraalVM. We are working with NVIDIA on a collaboration for better GPU integration. There is a talk about this also at this conference
On Thursday?
Thursday, right? So about GraalVM and CUDA, we have something that's called GR CUDA that will allow to offload any GraalVM languages onto the GPU, and we're working together with NVIDIA on that. We have an experimental WebAssembly frontend in the pipeline to also execute WebAssembly code on GraalVM, and we have that LLVM backend to support other architectures that are not so usual. Because currently on we have like x86 support, and we have some experimental support for ARM64. But all of these visionary parts, we will always have a pipeline in the GraalVM project about things that are still coming, not ready, but the core things on the left, they are 100% ready. And we believe in many scenarios they make a real difference. And one of the recent examples where it made a real difference is another large internal customer at Oracle. So at Oracle, generally, the Oracle Cloud infrastructure is moving to GraalVM Enterprise Edition to run the Java-based workloads for more efficiency in the Oracle Cloud and to lower the overall computational footprint. We have currently running more than 10 million core hours of GraalVM Enterprise in production. Probably now it's 100 million because this was like these numbers are like from 1 or 2 weeks old. And so we are running the largest services already in production with GraalVM Enterprise Edition. One of them is the Oracle Cloud Infrastructure Telemetry Service, where moving from the regular hotspot-based configuration to GraalVM Enterprise Edition in JIT mode gives a 25% reduction in garbage collection time and a 10% improvement in peak throughput. This is kind of in line with what we usually see for traditional Java applications, and for more modern Java applications, we are often seeing actually higher improvements than this. There's a little blog that describes the results at Oracle. Yes, there is also an Oracle GraalVM Enterprise Edition product nowadays. It has been a very long path for us to be on the official product page of Oracle, because with the product comes Oracle Enterprise Support 724. We do provide support directly from the GraalVM team, but we also cover the whole globe with the global support organization. Enterprise Edition offers higher performance, smaller footprint a little bit, and it also some additional security features. But most importantly, it comes with the support guarantees, and it's a true enterprise solution. And we are very excited that we not only have like a research project and some code out on GitHub, but we also have an associated product with it now, 100% launched. This product is, by the way, as we mentioned earlier, free for use in the Oracle Cloud. So, and the Oracle Cloud has a free tier now. So you can use the Oracle Cloud for free. I think you get a 2 GB instance, which should be about 16 GraalVM native images running there for free. And so you can. This is one of the things also you can try out. But generally, trying out GraalVM Enterprise Edition is also free on premise for evaluation use. You can just download it from the Oracle Technology Network and try it. Our versioning for GraalVM, so we kind of were going back and forth on this for some time in the project. We now settled on this versioning scheme that we think will fit most scenarios. We are doing major releases every 3 months. Every 3 months a major release, and it is scheduled on a fixed date. So you will know in advance. You can go to our website and look up when that release will come. And we participate in the regular critical patch updates of Oracle in the regular schedule. The last release of the year will become a longer-term support release that will be supported for at least 1 year afterwards. But generally, we do think that people should upgrade relatively frequently because we try to keep the compatibility between releases. We are working on more platform support. JDK 11 is scheduled to be released in 10 days from now. But we will have a JDK 8-based binary of GraalVM and a JDK 11-based binary of GraalVM. You can then choose which of those you like better. We are still working on ARM64 support and Windows support. There is no fixed release dates for those yet. Windows is supported in just-in-time compiled mode already, but the issues with Windows support is related to native image, where we can create native images, but we don't yet have the same amount of testing that would go into other platforms. Generally, we see GraalVM as a multiplicative ecosystem with several languages being like then, as Oleg demonstrated very nicely in the demo, have the same tooling for those languages, being able to leverage the same compiler optimizations, the same runtime optimizations, and then use this also not just embedded in the hotspot JVM, but embedded in other artifacts like node.js, standalone AOT, or Oracle database. So the next time you hear about GraalVM, etc., you should be able to kind of pinpoint which part of GraalVM are we talking about. Is it the ahead-of-time compile part? Is it the polyglot part? Is it the just-in-time compile part? So these are the three major areas, I think, where we currently have some innovation with GraalVM going on. And we certainly encourage people to add their own language or embeddings. We are working with various companies on this as well, most notably maybe Goldman Sachs, who recently gave another presentation at Oracle Code 1 about how they are porting their risk analysis language on top of the GraalVM platform for better support performance. Summary, the value propositions right now. First, high performance for abstractions in any language. For your Java application specifically, when you have a Spring application, certainly try it out on GraalVM JIT mode. We are looking forward to getting any type of performance results on that. Second, low footprint ahead of time compile mode for the low footprint environments. Third is the polyglot language interpretability. That is the third value proposition. And the fourth is that we are embeddable and we can embed other languages in your application. Right. And with that, I think we're at the end of time. Time's up. We took all the time. I hope you could get get something from the presentation. Download and use GraalVM. Give us feedback. We have a Slack channel now as well, a public Slack channel. We are very responsive on GitHub issues, or try to be so. Give us a follow on Twitter, so we can there we broadcast like only GraalVM specific news. And
subscribe to mailing lists.
Yes,
but most importantly, download it and try it.
Yes, and catch up somewhere on the conference. We were happy to answer more questions afterwards, also in one-to-one situations. With this, thank you all for your attention. Thanks for coming.
Thank you. Right, we're not muted actually. Oh, nice.